Hi, it's time for another math easy solution. Today we're going to go over further into vector functions and now look at motion in space and basically look at velocity and acceleration. Alright, and before we go further, as always, if you don't have time to watch this whole video, you could play this video at a faster speed, and top secret life hack, your brain gets used to faster speed. And here's a tutorial I did on the just downloading the browser extension and so on, so definitely check that out. And also you can also download and read the notes in PDF format as well as in article format on the Hive blockchain, and the link will be in the description below, as well as the video timestamps, so you can watch the video in parts. So timestamps of all parts are in the description, as well as the video sections playlist. And yeah, basically I'll be breaking down this long video into many smaller parts, put that all in the giant playlist, and so on. And again, with the timestamps, you can just skip ahead to wherever you want in this video. Alright, going further, so the calculus book reference. Note that I mainly follow along the book Calculus Early Transcendentals, 7th edition by James Stewart. There's a link to it. And for the whole chapter, I use the solution manual for this here, but for this video, don't actually use it for this video. But for the chapter, I use the link is over here. And the notes, and also note in some earlier videos, I used the 6th edition because I had the physical book there. Anyways, going further, so calculus book chapter. So the Hive notes and sections playlist for each video of this chapter are listed below. Yeah, so here's the whole calculus book chapter. There's vector functions, and this is a playlist to all of these videos so far. I've done 3 of these, so vector functions and space curves, and there's a sections playlist. This is the Hive notes, and there's derivatives and integrals of vector functions. And then the video before I did arc length and curvature, and now we're going to cover motion in space, velocity, and acceleration. And this is the current video, so it's going to be quite epic. And note that these links are also on MES links. If you go here to my website here, I basically added all these in there. You can click this button, and you can click the math tutorials, and then you'll see all these here. So you can shrink this, and so on. And then you go to the vector functions. It's going to be in here. So it's going to be like this. You can see them all there. In an infinite sequence series, I also have one spherical harmonics vectors and the geometry of space vector functions and so on. All right, pretty fascinating stuff. All right, going further, so topics to cover. Note that the timestamps will be included in the video description for each topic listed below. So we have motion in space, velocity, and acceleration. Go over example 1, moving particle in 2D, then example 2, moving particle in 3D, then example 3, integrating to get velocity and position vectors. Example 4, centripetal force, and then example 5, horizontal distance of projectile, and then example 6, impact speed of projectile, was actually impact on the ground. So tangential and normal components of acceleration, then go over acceleration vector in terms of derivatives of r, or the position. And then example 7, or in terms of, derivatives of the position. Of a position, like that. Or write it better, so in position vector. So acceleration vector in terms of derivatives of the position vector, and then look at example 7, tangential and normal components of acceleration. Alright, and now let's go finally into the chapter or the section. So motion in space, velocity, and acceleration. So in this section, we show how the ideas of tangent and normal vectors and curvature can be used in physics to study the motion of an object, including its velocity and acceleration along a space curve. In particular, we follow in the footsteps of Isaac Newton by using these methods to derive Kepler's first law of planetary motion. This will actually be in another video after this one, because remember, this one is motion in space. After that, I'll do an applied project on Kepler's laws. They'll be in a future video, so it'll be quite fascinating, so stay tuned for that. So let's continue for this. So suppose a particle moves through space so that its position vector at time t is r of t. So this is bold for a vector. All right, so let's say, suppose we had, let's say, here's the x-y axis. This is going to be the y. This is the x. This is the z. So this is in 3D. So let's say we had a curve that goes something like this. Okay, this is our curve C. And let's say we had a point P here. P, and let's say we had a point Q here. And what I'll do is I'll move this down a bit. Move it down like this tiny bit, so it goes down like that. Alright, so what we have here, I'm going to erase this, put this on top, like that, Q, and then this is, let's say we had, this is a position vector R of t, like this. Alright, I'm going to move this actually above it, slightly higher. So it's somewhere there, and also just shrink it like this a bit. And now we have, let's say this is the origin here. So this is the origin. Alright, so yeah, so there's the origin. I'm going to draw this line like this. This is going to be now r vector t plus h. So that's a position vector, and then this is at time. This is going to be at just increment by h the time, and it moves over there. Alright, and so what I'll do now is I'm going to draw this in red. So take this here, put this in red. Alright, so now what we're going to do is I'm going to draw this is going to be the tangent vector, so we're going to recall from earlier video. This is going to be the derivative, r prime of t like that. And that is the derivative there. And now this, I'm going to draw this one now in blue. In blue, let's put it like this. Let's just go this blue. Alright, so I'm going to draw from here, from P to Q. So this right here is a vector. This is going to be actually r of t plus h minus r of t. And yeah, so and you can see this because this, if you just use basic vector addition, so r of t. So if you take this one and then you add it to, then you add it to this one, what ends up happening is these just cancel out. So this would cancel out with this one. You're left with this. Yes, you're just left with that. Yeah, so we can basically erase all that. And yeah, so that's what we have there. And recall now again from in my earlier video on vector functions and so on, when we looked at derivatives. So if we extend this over here, so now this vector, and I'm going to draw this actually in black now. So I'm going to draw this in black. All right, and let's just close this part. So this one here, I'm going to, yeah, this one is just, we're going to multiply basically this right here by 1 over h. So we're going to multiply that by 1 over h, where h is the constant. Again, it's just this incremental thing there. In other words, it's just a constant multiplying by this. So the scale, so it's just going to be a scalar multiplied by vector. So it's still going to be parallel to this. So it's going to be parallel to this. It's going to be straight across it. This is going to be, and I'll just put an arrow. So this vector is just going to be r of t plus h minus r of t, like this, divided by h, like that. Alright, so now that we have this, and also I've had complaints about my drawing, so what I'll do is I'm just going to use the calculus book like image, and I'll just add that part there. And here, quickly just pause the video and added this over here. So here, yeah, it looks much nicer than what I drew, but I'm just going to draw this here, arrow. This is going to be our, yeah, this is going to be our r of t plus h minus r of t. Yeah, without the minus there. Yeah, and without the divided by h there. That's just this part right here. So this parallel to this right here, parallel. So anyways, going further, so notice from the figure above that for small values of h, the vector, and that's this part right here. So this vector, r of t plus h minus r vector of t. Yeah, this vector, and then just divide this by h, like that. Yeah, so this vector, this approximates the direction of the particle moving along the curve r of t. So as it's going here for small values of h, this is pretty much the direction of the particle. As this is like, imagine this h was super small, be right over here, and that vector will be literally pointing in the direction that this particle is moving. This particle is moving across like that, and that's going to be basically the direction of it. So its magnitude measures the size of the displacement vector per unit time. So in other words, yeah, this from P to Q, that's a displacement, and then this h, that's a time variable. So that's basically would have units of seconds if it was in seconds. So because you're going to be dividing it by this h there. So you're going to have displacement divided by time. In other words, you pretty much have the velocity. So the above vector gives the average velocity over a time interval of length h, and its limit is the velocity vector v of t at time t. So that's average velocity, but then at the limit, yeah, as h approaches 0, you basically have the limit of derivative. So in other words, yeah, what we have is the velocity vector v of t is equals to the limit of that displacement vector as h approaches to 0. So this is going to be r of t plus h minus r vector of t. divided by h, and now this just equals 2. Well, this is just derivative. So again, definition of derivative for vector functions. See that in my earlier video and video series. So r prime of t. So the velocity is just the derivative of the position vector, which is exactly what we already know in basic calculus. Yeah, so thus the velocity vector is also the tangent vector and points in the direction of the tangent line. So the speed, yeah, again, going back there again, here's this one here, this derivative as well as the average velocity, but then as the limit of h goes to 0, this gets shrinks and lines up with this right here. It becomes a tangent vector across there. All right, so thus, yeah, that's over there. So the speed of the particle at time t is the magnitude of the velocity vector, yeah, or the length of it, or the magnitude. That is the this right here, absolute value sign of the vector v of t. So this is appropriate because from the above equation and from the equation from my earlier video on the arc length function, we have. So recall from my earlier video. Here's a thumbnail of that yeah, one of these over there. So basically, this is the arc length function. Yeah, in my earlier video, I showed that the arc length right here, from here to here, this is basically equal to the integral of from a to t of the derivative of the velocity vector there. Because remember the position is essentially that's like the displacement or the position. So then the integral of the velocity, you'll get that position there, and I show that it's equal to this thingy. And then this equation is the one we're going to look at. The derivative ds over dt is the derivative of this position vector is equal to, again using the fundamental theory of calculus, that's the integrand part in there. So derivative equals to this, and then that's why if you take the integral, you're going to get the s. This one's going to be, well, the integral of that. That's this whole part. All right, so that's what we get, ds over dt on that. So what we have is, in our case, we're going to have the speed is the absolute value or the magnitude or length of the velocity vector, v of t, and this equals to, well, that's just going to equal to this part here, because we know the velocity vector is, yeah, this one, the velocity vector just equals to the derivative of the position. So that's just going to be, or the tangent vector, that's the tangent vector, this equals to the absolute value of r of prime of t. And now this is equals to ds over dt from our earlier video. So ds, that's the arc length, etc. So ds over dt. All right, and then writing this out, what this means is basically, well, this is just rate of change of distance with respect to time. Yeah, I'll put it all like that, respect to time. And again, calculus will put it all in one like equation form, so I'm doing that as well. All right, yeah, so that's what we have there, and again, that's the ds over dt. Again, it's just infinitesimal small change in distance divided by infinitesimal small the time there. So basically, this right here. So, but like super tiny, ds over time. Yeah, so something like that. Or yeah, it's pretty epic stuff there. All right, and just as in the case of one-dimensional motion, the acceleration of the particle is defined as the derivative of the velocity. Yeah, so to get the acceleration, well, it's just going to be the a vector, like that acceleration vector. This just equals to the derivative v prime. Yeah, this is it is better. So v vector derivative of that respect to time divided by this is going to be, actually I'm not dividing anything yet. That's just it, like that. Yeah, just the derivative of the velocity vector, and then this is going to equal to now, well, remember this one right here, so the velocity vector is equal to the derivative of the position vector, so in other words, it's the second derivative, so just double derivative of the position vector r of t, like that. So that is quite fast. I'm going to actually bold this because this is pretty important. Yeah, so we bolded this one right here. I'm also going to bold the velocity here too, because this is pretty big formula that we're going to be using. That's velocity one. Again, it just equals to using definition derivative, and then you get this part right here, derivative of the position vector, and then the velocity acceleration defined as the derivative of the velocity, or the second derivative of the position vector. All right, and now let's take a look at an example on this. So example 1, moving particle in 2D. So the position vector of an object moving in a plane is given by r of t equals t to t cubed I plus t squared j vectors. These are just the standard basis vectors. So this is the x component, this is the y component. So we're asked to find its velocity, speed, and acceleration exploration. All right, here, just fix that up and illustrate geometrically. All right, so remember, in a plane, this just means in 2D. And then we're given two dimensions right here, I and j, or x and y. So solution, the velocity and acceleration at time tr. So that's r of t. So what we'll do is, we're going to write here is the velocity is going to be the derivative, r prime of t. That equals to, derivative is going to be, there's the t cubed. So it's going to be, take the derivative, so 3t squared I plus, and then 2t. The t squared becomes 2t, the derivative. This is going to be j vector. And then likewise, the acceleration, this is going to equal to the derivative of the velocity, which is the second derivative of the position vector. So this equals to r double prime t. This equals 2. Now take this down, it's going to be 6t. So put the 2 down and subtract 1 power. So yeah. 6ti plus, and this is going to be 2j, like that. All right, and the speed now, because we're asked to find the speed as well. So the speed is obtained from the length or magnitude of a vector formula. Yeah, so this whole thingy right here. Or actually, writing it a bit better. So, and the speed is obtained from the formula for the length or magnitude of a vector, which I showed in my earlier video. Again, it's distance formula in 2D, in 3D, and 2D actually, because if the z one is a 0, just get rid of it all. Yeah, so that's just going to be like this, and this is just basically using Pythagoras. So the distance from P1 to P2 is equal to x2 minus x1 squared plus y2 minus y1 squared. And then in our case, that's 0, so just ignore that. And then all square root. So thus the speed is the, right here is the absolute value sign there. So speed, and I'll write this down as speed. So just the magnitude of the vector velocity vector. Of the velocity vector. It's the magnitude of the velocity vector. So this equals to, this is the magnitude. This is the v. So v vector I got of t. This is going to equal to now square root, and then we just take the components. So 3t squared and 2t. So we have to square those. So it's going to be 3. Put this for completeness for this first example. So 3t squared plus, and then 2t squared. 2t squared, and we're going to square root all that. Like that. So this is going to equal 2 now. This is going to be just simplified. This is going to be 9. So 3 squared is 9. 9t to the 4 plus, now we're going to have 4t squared. All right, now the next setup is, when t equals 1, and again, this is actually forgot to include this. So find its velocity, speed, and acceleration when t equals 0. And illustrate geometrically. So, all right, so when t equals to 1, we have, let's get all these values here. So we have a v of 1. This equals to, look at our velocity right there. This is going to be 3t squared, so 1 squared, and then plus 2t. That's just going to be, 3i plus 2j. All right, and then the a value, that's just going to be the acceleration. I'll put it like this, actually. So acceleration at 1, this equals 2. Well, plug that in. So this is going to be, 6 times t times 1, so 6 and 2. So that's just going to be 6i plus 2j. And then lastly, the speed. So this is going to be the velocity, the magnitude of the velocity at 1. Is equal to, let's plug that inside. So we're going to get a 9 times 1 plus 4 times 1. Squared doesn't, 1 squared doesn't change anything, so 1. So this is 9 plus 4. That's equals to square root 13. All right, so now let's draw these out. So these velocity and acceleration vectors are shown in the figure below. So what we'll get is, we have to go back to our position vector. So r of t, this equals to, just to see how it would look like, this is a t cubed I plus t squared j. So this is going to be t cubed I plus t squared j. Yeah, so notice here, so basically for negative values of t, what we end up having is, oh, well, this is going to dominate right here. It's going to be negative. Oh, actually, no, we're dealing with parametric, yeah, these are I and j. So for negative values, the x component, this is the I one, that's going to be negative. So in other words, we're going to have something like this. But we're going to ignore the negative side mostly. So I'm going to go, this is x, this is y. So for negative values of t, we're going to have negative values, but then this right here, this is the y component, the t squared, or the j component, is always going to be positive. So it doesn't matter if you go negative, it's going to be like it's always going to be positive, and this is on the squared side, so it looks like a parabola. So basically it's going to be like parabola-like, but then you have this t cubed there, but it's going to look something like this. And what we'll do is this is going to be the origin. So we're going to ignore the negative sides more. And now at the point, and also if you plug in 1 right here, so this is this right here, r of 1, this just equals to, well, 1 yeah, I plus j. Because, yeah, the t squared or t cubed is just 1. So that's just going to be 1, 1. It's going to be somewhere here. Yeah, so that's our 1, 1. Yeah, so I'll put that like this, 1, 1. And then the tangent vector is going to be, I'll draw this in red. Yeah, I'll go over here. I'll draw the tangent vector in red, or actually I'll draw that in blue because the calculus book does it. So this is the tangent vectors like this. And this is going to be right here. This is 3i plus 2. Yeah, it's going to be something like that. But regardless, this is going to be our velocity of 1. This is at the 1 point right here. It's 3 plus 2. So it's going to go 1, 2, 3, and then up 2. So 1, 2. It's going to be something like that. And I'll draw it now in red. This part right here, the acceleration. The acceleration is going to be, it's going to be more flat. So it's going to be 6 and then 2. So in other words, it's going to go 6 here and then 2 up. And what I'll do is I'm going to move this down. Move this down like that. And yeah, actually I moved that above there, so move it over there. So now to draw in the red one, it's gonna be flatter, so it's gonna be something like that. And this is gonna be our a of 1. And this is gonna be a vector. So put these vectors. It's gonna be 6 to the right and then up 2. The other one's gonna be 3 to the right and up 2. So it's basically like half the steepness over there. And what I'll do is I forgot to draw this part. And this is going to be the arrow on top. So that is that. And I just fixed it up, made it darker there. All right. So that is the vector there. Yeah, and likewise, I'm just going to just use the figure in the calculus books. It's just, it gets more accurate. I'll just use this figure. So here's the figure from my calculus book. And yeah, there is our velocity and acceleration vectors at 1. And for completeness, as always, I like graphing this out in an online calculator. In this case, let's also graph in the GeoGebra 2D graphing calculator. So here it is, and I made this a pretty epic calculator right here, or I mean this little section of the calculator. So I added this, made it customizable, and so on. So there's our curve. You could just write curve equals t cubed t squared, and then made it from -10 to 10. And so on, and then you can adjust the slider here, A, and yeah, so you can adjust that slider. I'm not sure what this R of A is. I think I can remove that. Yeah, so then we have the point P. So that's the point. There's a position vector here, like that, and I will draw this in black and get rid of this thingy. Yeah, so this is our position vector, and then I also have the velocity. Velocity is equal to, well, the position vector plus velocity plus p, and where velocity is just this. It's 3a squared plus 2a. That's just this part right here. I made it generic. So 3a, yeah, 3t squared plus 2t, and I put a so that I can have an a variable I can change. So this is the curve. So this is the curve. It will draw this fully out, but then I want to point with the vector always there. So I made a second variable a so I can modify this. A is just for t. And then likewise for acceleration, we have 6a 2. Yeah, so 6a, so 60, and then I can modify it and so on. And again, this a, p, and this ra, I'm not sure what those are actually. I'll see. I might actually just remove them. Anyways, then you could slide them over and see what happens. I'm going to open this up and let's see how this looks. So I'm going to open this up, make this wider. Yeah, just I just want to load in real time so you can see it all loading. Let's see. Okay, it's taking a while because it's probably on the tablet. All right, so there it is. And yeah, it looks pretty epic, actually. I'm just going to drag this around and then drag this around. Move the A up top. So this part right here, I don't even know what this is for. Oh, that's AP. I'm going to delete this, actually. And then this other one. Where was the other one? We had another RA. So what in the world is RA? I'm going to delete this. Yeah, so delete those. All right, and yeah, so and now I'm going to, yeah, it's recording. I think I accidentally put a 1 there. Anyways, Control Z, I'll just leave that. Yeah, so anyways, so what we have now, there's our A. You can either slide it from here, but I also put the slide, you can also show the slider here. So you can actually slide it. It's pretty cool. So you go to A is 1, so we have this point 1, 1. And there's a velocity vector, and again, the velocity, the acceleration vector is just P plus ACC plus P. So this point, this is the vector, I just add it to the point P. So that's how you make it. So it looks absolutely amazing. Yeah, there it is. it's quite fascinating there. And notice how at 0, they're pretty much the same, or acceleration is actually 0. Yeah, so at 0, velocity is pointing upwards. Acceleration is 0, and now it's gradually building up, and now it's going faster. And then speed picks up as well. So that's quite fascinating how it is. Yeah, anyways, and this is the negative side, goes like that. All right, anyways, play around with that. So let's close this. Leave, all right. All right, and here I quickly pause the video and I just updated that whole thingy there, updated the screenshot, but I also removed that, earlier I had that ACC, etc., and the velocity vector, and I just put them inside this vector formula. So I have, basically you can go into the GeoGebra and just write acceleration equals vector, and then it starts from the starting vector is P, and then to the point, this is our 6A, and then 2, that's our acceleration now. And then just add it to the point T. So that basically goes from here and then puts this vector from like that. So this point right here is going to be the 6A2 acceleration plus P, the ACC. And then likewise for the, I made it here so compact, make it more compact. So velocity is just equals the vector from P and then to the point 3A squared, again, A instead of T, so I can make it variable. And then 2A and then plus the vector there. So this part right here, it's velocity plus, so this is the velocity one, and then you just add it, so you start from here and then goes all the way to P plus this velocity. P plus V. All right, so pretty amazing stuff there. Anyways, let's continue further. All right, so now let's continue further and look at example 2, moving particle in 3D. So this was in 2D, example 1. Now we're going to take it a step further in 3D. So find the velocity, acceleration, and speed of a particle with position vector r vector of t equals 2 and has components t squared, e to the power of t, and then t times e to the power of t. All right, so let's take a look at the solution. So the solution, well, we take the velocity of this. The velocity is going to be the derivative of that, so it's going to be r of, the derivative of the position vector, r of t, so then put this all inside. It's going to be now t squared. The derivative is going to be 2t. Then et is going to be, well, et, that's a special property of the exponential number e, or just a number e to the power of t. And it's used a lot because the derivative is itself, instead of having to deal with logs or lns and, logarithms and so on. So it's going to be now t, derivative of t using product rule is going to be, well, derivative of t is 1. So we're going to have et, and then derivative of plus now t times derivative of et is et. Like that. And now this equals 2, just put it like this. This is going to be 2t et, and then this is factor out the et, so it's going to get a 1 plus t, 1 plus t like that, and then e to the t, like that. Fascinating stuff. All right, and now the acceleration, well, we're going to take the acceleration, is going to be derivative of the v, or the second derivative of our position vector. Okay, this equals 2. Yeah, actually, we take second derivative of that, or the solutions put actually v right. I'll just copy what it had. So v derivative of the derivative of the velocity, and that's just going to be the second derivative of that. This just equals 2. Now take the derivative of this one. It's going to be 2. And then e to the t is just e to the t. And now this one right here, again, likewise, the derivative of 1 plus t is going to be, well, this goes to 0. We're going to have a 1. We're going to have a e to the t. And then again, likewise, plus 1 plus, using product rule and derivative of et. It's going to be e to the t. Like that. So factor that out. We're going to get a 2 e to the t, and then we're going to get a setup like this. This is going to be now plus, yeah, this is factored this out. We're going to have a 1 plus 1. In other words, we're going to have a 2. 2 plus t e to the t, like that. Alright, and now let's get the speed, and that's basically the magnitude of the velocity vector. So we're going to get the magnitude of the velocity vector, and using our giant square root squared everything. So we're going to have a giant square root sign like that. Now 2t squared is just going to be, well, 4t squared. And now et squared is going to be plus e2t, and I'll write this a bit bigger, 4t squared, and then plus the last one, this one right here, 1 plus t, and then squared, 1 plus t squared, then e to the 2t, so that gets squared as well, e to the 2t, like that. Alright. Yeah, alright, so we're done this question, but the calculus book keeps going further. So it draws the figure. So the figure below shows the path of the particle with the velocity and acceleration vectors when t equals to 1. So I'll try to draw this out manually, then I'll just show the, I'll take a screenshot from the calculus book. So, or just take the figure from it. So what we'll have is, so let's say we have our, this is going to be our x. This is going to be our y setup. I'll make the y like this, actually. That. And there is our z. So now we take our position vector. Let's go start from the beginning. This one right here. So r of t. Yeah, so put it at 1 initially. I'll just put the whole thing. So r of t is equal to t squared et. Yeah, so it's going to be t squared. Yeah, because I like trying to draw it out manually. Just it helps you understand how the equations all plays out. So t and then et. T, E, T, like that. So then R of 1, well, it's going to be, plug in 1 inside here. We're going to get a 1, so T squared is 1, and then E to the T, actually, yeah, this is going to be just E to the 1. It's going to be E, then the other one's going to be E as well. It's going to be 1, 1. And then also I want to get is the starting point. I'm going to actually put, notice what we have is R of 0. This equals 2. We'll plug in 0. We're going to get 0 for the x component. Then e to the 0, that equals 1. Then it's going to be, well, 0 times e to the 0 is still 0. This is going to be, by definition, 0, 1, 0. So that's our starting point. I'm just going to only graph the positive values of t. So we're going to go right here and put in this part right here. So 0, this is origin there, 0 there, and we're going to go to 1. So that is 1. On the y-axis and 0 on the z-axis, and then afterwards is all positive. This is just going to be e to t squared, e to the t, then t, e, t. So it's all going to be positive. It's going to be basically increasing. It's going to be something like that. Yeah, something like that, and so on. All right, and now because it wants it at the point, basically at t equals to 1. So let's take a look at that. Yeah, all right, so the velocity at 1, v vector at 1 equals 2, and that's this part right here. And where is it? Yeah, this velocity. So 2t, so 1, so be 2, then e to the t is just e, then this one here, 1 plus t, e to the t. So in other words, that's going to be 2, 1 plus 1, e. So we're going to have a 2, e to the t is just 1, then 1 plus 1 is going to be 2e. Like that, and then the acceleration is at 1 is going to equal to, well, pretty much the same thing as the velocity, right here, because this was number 2t. This goes to 2, and then this is e to the 1. This is e, and now we have over here 2 plus t. In other words, 2 plus 1, so it's going to be 3. Then e to the 1. So we're going to have a 2e, 3e. So it's exactly the same thing as the acceleration. I mean, as the velocity, except the z component is higher, so it's going to go up faster than the other one. So we're going to draw. I'm going to draw this one in. Yeah, I don't know why calculus book keeps drawing it in blue. So it draws the velocity in blue. It's going to be something like this. Let's say we have it at t equals 1 here, and you have it, and it's going to be always tangent. So this one's always tangent. So that is tangent. So this is v of 1. I'll put it here. put it here like this. Actually, I'll just keep it like that, and then I'll draw it in black after. So yeah, so I'll draw this right here. This is going to be v of 1. Yeah, the calculus books. Yeah, the calculus book just does that. So I'm going to draw now in red, and the red is going to be well, it's going to be the same direction as the v, except it's going to go faster up. So it's going to be actually faster up. So magnitude is going to be slightly bigger as well. Yeah, it's going to be up like that, and this is going to be our. I'll make it like that. Yeah, this is going to be our. I'll just put it like this in red. Okay, so this is going to be a vector like that. Yeah, so that's going to be more vertical. And at this point right here, I'll make it in black. This is at our t equals to 1. And again, notice how t equals to 1. We have 1 EE. So we go to x is 1. So it's going to be actually like this. X is 1. So this is going to be x is 1 there. Yeah, that's 1. X is 1, then EE. So it's going to be this number. It's going to be somewhere around here. E is 2.618 or something like that. And then, yeah, then the other one's going to be E above as well. This is 2.618. It's E, yeah, so it's E. Yeah. So that's pretty fascinating stuff. All right, here, quickly pause the video and just Googled E equals. So E is actually at 2.718, not 618. All right, so that's pretty close. I also thought it was 618. Okay, so I guess it's 718. Anyway, so that's what we have. And what I'm going to do now is I'm going to erase this and then just use the calculus book drawing because it's neater, and then just write over it as well. So that's what we have. I'm going to close this part here. All right, yeah, so that's what we have. Yeah, so it's, again, much neater. And now what I'll do is I'll write down the stuff that we want. So this is going to be somewhere here, and this is going to be at our x is 1. So I'll write this like this. This is x is 1 here. That's our 1 EE, and then we're going to get all the way across here. This is going to be at our, I'll draw this at E, and this is, again, it doesn't look like it's to scale either, so that's interesting. So yeah, drawing isn't that well. It's going to be like this, to 1, 1, 1. I'll draw this a bit better. One more. Okay, let's try it again. Dash 1 dot like that. Yeah, so it looks something like that. Yeah, so it's pretty fascinating stuff there. And now we'll graph this in GeoGebra to see how it actually looks like. But I also have t from -10 to 10, but again, you can typically ignore the negative values there. Yeah, and yeah, that's typically because time, yeah, time just moves forward always, so you don't have a negative time and so on. But nonetheless, I do graph it in negative just to see how that looks like. But anyways, let's click over there. I'll do that soon. But so there's the graph, and then there's our a value. You can adjust this. If you go to a equals 1, and it will get you this setup here. You can also go to a equals 0 to get to the bottom there. I'll graph it out soon. Again, as before. So here's what I did. So here's I made the point A as R of A, the position vector. So I put this inside this one at A there. So where A, you can make it a variable. So you could this will put it as 1, 1.2, and so on. All right, so that's A. And so then the acceleration as before, I go, the way you would write it, you go vector A plus, so you're going to have a displacement one. So you go from the A point and then over to this vector acceleration. And then there's acceleration, so we're going to have it as 2 e to the power of a, and then 2 comma ea, and then comma 2 plus a to the power of times e to the a. Again, you put t, so it graphs out the whole thing, then a for specific points, and this is a vector, and then plus a. And then likewise here for the velocity, you go vector a, and then a plus, there's the velocity vector 2a, 2a e to the power of a, and then 1 plus a. E times e to the power of a. Again, that's just this part right here. So this is 1 plus t or 1 plus a. This is 2 plus t or 2 plus a, and then everything else is the same. 2. Well, yeah, this one's actually 2t. This is 2, and then et. Yeah, so that's the difference as well. So 2a. So there's the 2a for velocity, and then you have multiplied. I'm going to take the derivative 2 for the acceleration. When you get something that looks like this. Like that, and it looks just like this part right here, and we're going to graph this out. Let's play around with it. Alright, so I'm going to close some stuff. Yeah, so it's going to load up. Yeah, so there it is, and it's there's our setup, and you can adjust this, make it at 1. And yeah, you could adjust that, you could make it there, and you could also show it. So what you could do is, so you can move this like this. Goes down, let's go to 0. Where does 0 go to? Yeah, so 0 goes to the y-axis at 1 there, so that's pretty cool. And then make it at 1. Looks like that, where it's literally parallel to, or like, yeah, parallel to it. Actually, well, parallel from the other side. But yeah, basically it's in line with it. It's the same plane. I mean, not parallel, but actually, I would say it's like, yeah, basically the same thing except it's pointing upwards. So yeah, a better way to state that. So it's basically, this is just a bit higher because you have the 3e. This one is 2e there. So that's pretty cool there. And then what I'll do is just see how this graph will look like. Just play around with it and say, let's say we go from here, instead of -10, we go to 0 and then go to 100. See how this looks like. Yeah, it goes like that. Okay. So this is it's just going to be pointing up more and more. Is there a way to shrink that? Okay. Shrink it there. I'll make this shrink. Oops. I'll shrink this there like that. Okay. It goes up. Anyways, it will look something like that. And what I do want to do is go back to this negative side. I'm going to go undo. Get the negative sides in there. Okay, so there's the negative sides. Yeah, so the negative one looks like this. It's pretty interesting. It goes underneath there. And so on. That's pretty cool. And it's, I think I would assume it goes to 0, close to 0, because you're having this, this part right here, e to the t, but now if you have e to the negative, it's going to be the same thing as writing 1 over e. So you're going to have a dividing by a big number. Same thing with here. So the y and z components get shrunk, whereas this one just becomes positive anyways. So anyways, that's pretty fascinating stuff. Alright, and now let's continue further. Now look at integrating acceleration and velocity vectors, and we'll illustrate this with an example. So the vector integrals that were introduced in my earlier video, here's a link to that, can be used to find position vectors when velocity or acceleration vectors are known, as in the next example. And again, here's the recap. This is a thumbnail of that video. And then there is a thumbnail of the section in this video. And all these will be in the link over here. And so basically, just to recap, so just recall the derivative of the position vector. You could use this the definition of derivative, and you could also do it by component. So the derivative of this equals derivative of each x, y, z, or I, j, k components. Like that. And same thing with integrals, as I showed earlier. So the integral is going to be the same thing. Integral of the position vector is equal to the integral of each component. So there's the I, there's the j, there's the k. Yeah, there's I, j, k. And then that equals to this one here, capital R of t. That's the antiderivative, where antiderivative is the derivative of that capital R is equal to just R of t. So that's just what the antiderivative is, and then you evaluate it just like regular integrals. And yeah, here's the thumbnail for the other one. And again, this is the same setup as normal integrals. And there's the you sum up into infinite rectangles like this, and yeah, and then you do that for each component. Yeah, so you do sum of infinite rectangles for the I component, the j, the k, and then basically as the limit as that n approaches to infinity, as the amount of rectangles and so on, you get the integral. And again, there's this whole setup here. Anyway, so let's illustrate this with example 3, and that's integrating to get velocity and position vectors. So a moving particle starts at an initial position of r right here, r of 0 equals to 1, 0, 0, with initial velocity. Yeah, here I just wrote that in. And so with an initial velocity of v vector of 0 is equal to I negative j plus k. Again, these are standard basis vectors. Again, in coordinate format, or this would be like this. 1, negative 1, 1. Yes, that's what it is. Anyways, just keep it like that. It's pretty straightforward. All right, so in its acceleration, it's given by a of t equals to 4ti plus 6tj plus k. And now we're asked, find its velocity and position at time t. All right, so let's take a look at the solution. So we were given the acceleration, and now we're going to move backwards. We're going to go get the velocity and position. Before in the previous examples, notice what we had. We were given the position, and then we take the derivative to get the velocity, and then derivative again to get the acceleration. But now we're going the reverse way. Now we're going to go acceleration to velocity, then velocity to position. And that's using integration. All right, so let's take a look at the integrals of that. So let's say we're given, so since we know that a of t, that acceleration is equal to v, the derivative of the acceleration of the velocity, v prime of t, then, yeah, so we have that, so then this is going to be v. V of t. The velocity is equal to the integral of this is of the acceleration. Yeah, because we have this derivative to take the integral to get the regular velocity. So we're going to get now, this is going to be the integral of, and then we have the acceleration is going to be 4. I'll put a bracket like this, 4t. I should put a normal bracket, not a square bracket. So 4ti plus 6tj plus k, like that. And this is going to be now, this is going to be dt, like that. Alright, here, just fix that up. So now take the integral of that. This is going to equals to, well, of each of these components. We're going to get, now this is going to be a integral of 4t. That's what we, for t squared, and then move a t divided by 2 there. So it's going to be 4, 2. Because if you take the derivative, put the 2 down, it would be 4, and then t power of 1. So 2ti, like that, plus, and now we have this one, t squared, then divided by 2. So this is going to be, yeah, let's delete that. This is going to be t squared divided by 2, so 6 is going to be 3. Yeah, 6 divided by 2, like that. The next one is going to be, well, plus just t, like that. T, and this is going to be, yeah, this is, we forgot the j component, and then plus t k component. And now we have to have an integration vector constant. We're going to call this vector c, because this is the, if you just have a vector like this, and then the derivative of that's going to be 0. So you have to have that a constant like that. All right, and now going further, so to determine the value of the constant vector c, we plug in our given value for the initial velocity. So v, v vector 0. So this one right here, and we know that the initial value we're given is initial velocity at 0, t equals 0 is equal to I negative j and then plus k. So let's write this out. So we're gonna have v of 0 equals to, let's write this out, I negative jk. I vector negative j vector plus k vector, like that. Now this equals 2, and now we just plug in t equals 0 for all this. And then so we're gonna have a this is gonna be a 0. So we're 0, let's put a 0 like that. Plus there's another 0 plus another 0. So yeah, plus c. So in other words, c, the c constant, vector constant of integration is equal to just the initial velocity, v of 0, and this just equals to I negative j plus k, like that. Yeah, so thus our velocity right here, we just plug in the value for k there. So thus, yeah, I'll put it better, thus v, so that's what we have is v of t is equal to, let's plug these in, so 2t squared I plus 3t squared j, and then plus t k, and then plus, this is going to be, well, I negative j plus k. And these are just the components, so we can just add these up accordingly. Yeah, so we're going to add up the k components here with this. Oh, not that one, with this one. With this. So we're going to get this equals 2, well, put a bracket, 2t squared plus 1. So just factor out the I. Like that. This is going to be I component. And now likewise here, this is going to be plus 3t squared minus the j one, so minus 1. Let's factor out that. This is going to be the j component. And then lastly, it's going to be t plus 1. So it's going to be t plus 1 k, like that. Alright, so yeah, that's what we have. Let's bold this whole thing in for our velocity. Yeah, so that is our velocity vector. Yeah, so now the next setup is, now we just do the next one. So since, to get the position vector, since r of t is equal to, well, actually not r of t, the other way around. Since the velocity of t is equal to the derivative of the position vector, yeah, so since we have that, so again, pretty much the same thing as before. Likewise, the r of the position vector is going to equal to the integral of v of t. dt, like that. So yeah, make sure to put a dt there. Let's see if I put a dt over here earlier. Yeah, this one a dt. Yeah, here I just fixed that up. Yes, added the dt there. All right. So again, just leave it like that. So now this is going to be this is going to equal to, well, integral now of this whole setup there. So we're going to have a, I'll put a square bracket. Yeah, square bracket. Now we have a 2t squared plus 1. And then this is going to be, it's going to be the I component. And then this is going to be plus 3t squared minus 1, this is the j component, and then plus 2t plus 1 k component, and then put this whole thing bracket and this dt now, like that. All right, so now let's just evaluate this to the integral of each component. So this 2t squared, well, that's going to be t cubed, then we divide it by 3, well, it's going to be just 2 over 3. And now the next one's going to be the integral of 1 is just t, like that. So that's what we have. This is going to be, I'll make this less dark, 1. Yeah, I mean plus t, I'll just fix everything up. So this is going to be I. Now the next one's going to be here. This is going to be, well, t cubed, and then divided by 2. So it's going to be 3. I mean divided by 3. Yeah, so 3 over 3 is just going to be cancelled. So we just leave it t cubed. Like that, yeah. And now the next one's will be, well, minus t, like that. This is j. And now plus, next one's going to be, well, t squared over 2, like that. Yeah, t squared over 2, and then plus t. And this is the k component. Yes, that's what we have. And actually, we need to include the integration constant. So I'll put a plus d vector, because we already took c before. And I'll just move this over. I'll move the whole thing over, actually. This whole thing, I'm going to shift it over just to fit my little box here. Because I have this line here, just to make it nicely, here, this line. Alright, so that's what we have. Alright, so likewise, using our given value for r of zeros, or just the initial position at t equals 0, to solve for the integration constant vector, we get... And again, that's if you scroll back up here, we're given this. So the initial position is 1, 0, 0. All right, so let's put that in. So this is going to be r of 0, t equals 0 equals to 1, 0, 0. Yeah, now this just equals to, in our ijk format, this just equals to I. And then all the j and k are 0. And now this equals to, now if we plug in 0 into all this. So these are all t, so this becomes 0 there. Plus another 0, this t cubed minus t, plug in 0 for everything. This one is 0. And then plus, well, d vector. So again, notice what happens. D is equal to, the d vector is equal to, well, just the initial position vector, r of 0, which equals to I, like that. Yeah, so then we just add I to this one here. So all we do is add a 1 there. So thus, the position vector, r of t, is equal to, well, the whole thing, I'm just going to move my mouse here, so I'm going to put it like this. 2 over 3, t cubed plus t, and then plus the 1, the I. So that's all, plus t plus 1. So that's the only difference that we have there. And then plus, and then t cubed minus 1, I mean minus t. J plus, and then last one, t squared over 2 plus t, and this is going to be our k. Yeah, so that's pretty much it. So we could box this whole thing in, make a better box. Perfect. All right, going further, so the expression here for this position vector, r of t, that we obtained in example 3 was used to plot the path of the particle in the figure below for 0, so 0 is less than t is less than equal to 3. So where t is between 0 and 3, like that. So here's the figure from my calculus book, and I'm going to graph with the GeoGebra, but before we get to that, so we're given the initial point 1, 0, 0. And now this last point here, so that looks, this looks like it's like 8, I think. So we'll just look at this point right here, at this point. So at t equals 3, So at t equals to 3, let's just look at our actual position vector. That's this part right here. And what we get is, well, we're going to get a, so at this, we're going to get a r of t. Now, r of 3 is equal to, well, this is going to be 2 over 3. And then this is going to be 3 cubed. That's 27. Because this is just 3 times 3 is 3 times, this is going to be 3 times 3 times 3. So that's going to be, this is going to be 9 times 3 is 27. So 3 times 3 is 9, times it by 3 is 27. All right, so it's going to be plus 3 plus 1. And this is going to be our I component. All right, for the j component, that's just going to be plus, and then this is going to be, well, t cubed minus t, so that's going to be 3 cubed minus 3, and this is going to be our j component. And then lastly, the k component is going to be, well, 3 squared divided by 2, and then plus 3. Like that. This is our k component, like that. Yeah, so let's just evaluate this. So this is going to be, well, the top part's going to be, we can cancel one of these out. So cancel the 3 with, this becomes a 2. So in other words, 2 times 3 to the power of 2, that's 9. So 2 times 9 is 18. So 18 plus 3 plus 1. So in other words, 18 plus 4 is 22. So 22i. And again, notice here, 22, there's a 22 there. Yeah, so it goes to x on the 22 side. And then the next setup is, so the next one is going to be the j component. 3 cubed is 27 minus 3 is 24 then. 27 minus 3 is 24. Yeah, j. So we have, this is 22, and this is, the 24. So 24, and 22 on the other side. So the y is 22. So that is that. So the next one should be around 8-ish or so. So it's going to be now plus 3 squared is going to be 9 divided by 2 is going to be 4.5 plus 3 is 7.5. All right, so it was close to 8. And you can see right here, it goes to 7, and then there's a 0.5, 7.5. Yeah, so that is the height of that. So right here. So there it is. That is that part here. It's fascinating stuff. Yeah, let's leave it like that. So I just wanted to put that at t equals 3 there. All right, and now let's also graph this in the GeoGebra 3D graphing calculator, just so we have the equation there. We can look around it and view it in 3D and so on. And again, it's pretty cool to work with it. And again, here is the setup here. So I have the variable a equals 3, just so I could move along the curve. So here's the curve r equals, and this one here, I can vary this a equals 3. I can move it around back and forth and so on. And now we have the curve. This is going to be 2 over 3 t cubed plus t plus 1, and then t cubed minus t, and then there's this 1 half t squared plus t. And again, that's just this whole setup there. And then I have the t from 0 to 100 and so on. So now we have the starting point a. I just put a equals to r of a. Well, actually, no, it's not a starting point. It's just the point on it that I'm going to take the vector from. And initially, this is the a. This is at t equals 3. And again, notice that t equals 3, what we have is, well, 22, 24, 7.5. So we have this 22, 24, 7.5. So exactly what we just solved there. That's for this a, where a is 3. Yeah, so now what we have is velocity. I have the velocity vector is starting from a and then goes to a plus, now we have the velocity vector there. So 2a squared plus 1. And then 3a squared minus 1 and a plus 1. A, where a is just our t, but we're just manipulating the a. So this is going to be, again, that's just the velocity one going back up here. So 2t squared plus 1, 3t squared minus 1, and t plus 1. We're just replacing t with a. All right, and now the last one is acceleration. That's just equals to, again, vector from a to a plus, so a to a plus 4a 6a 1. And that's right here. Going with this velocity, and the acceleration, well, again, acceleration, we're given this. Acceleration is this, 4t, 6t, 1. In other words, 4a, 6t, 6a, and then 1. Yeah, so that's what we have, and then there's a graph like that. So you can see this is, it looks exactly like that setup we had over here. So it looks exactly like that. And let's just play around with it, and it's already opened. I'm going to go over here. So here it is. I'm going to actually save this, because I used it. Yeah, so anyways, I had to fix some stuff up. But anyway, so that's how it is. And you can see this. Now if you go to r is a 0. I go to 0. I'll move this, I don't like this thing, make it 0. Alright, so it starts off at 0, enter. Yeah, so, it's like I made it 0, it doesn't do it. Okay, so 0, yeah, so 0 is the beginning, and notice at 0 is 1, 0, 0. So again, that's exactly what we had, what we should have, and then notice that the velocities change. I mean, the velocity and acceleration vectors, again, absolutely amazing, and it follows all the way along. Go to the 3, and then we have the values calculated, 22, 24, 7.5. And zoom out, and there it is. Yeah, absolutely amazing stuff. So again, play around with this, and yeah, that's why I actually I like doing this because you literally see, and you could validate that your equations are right because you can literally see a graph in 3D like that. It's pretty amazing stuff there. I'm gonna close this and leave. All right, epic stuff. And yeah, so to summarize all this, well, in general, vector integrals allow us to recover velocity when acceleration is known, and position when velocity is known, and we could write this out as, the velocity. So if we have acceleration's velocity, v of t, is equal to, and again, remember how our our integration constant for velocity, this part right here, the c just equals to the initial velocity, v of 0. And then likewise for the position vector, the integration constant was just equals to the initial position there. Yeah, this initial position at t equals 0, because all these vanish. So typically, that's what the case we have. So in general, this is what we usually have, and this is going to be a equals to v at t naught, or the starting position. So I'll put that instead of t equals 0. Sometimes you start off at different positions. So t naught plus, yeah, so at a specific point there, and then this is going to be from t naught to t of a, and we're, the acceleration one, and we'll use a different variable u for the du, just so we can for the integration, just change the variable there. And then for the position vector, this equals to, when velocity is known, this is going to be equals to the initial position at t naught, because we're going to be taking integral from t naught to that. So typically it's t equals 0, but not always. So we're going to go t naught to t, and now we're going to have the v velocity, the integral of that vu du, just so we have a different variable. Because we have the t there, we're going to plug the t inside. So yes, absolutely fascinating stuff there. Alright, now let's cover Isaac Newton's second law of motion. So, if the force that acts on a particle is known, then the acceleration can be found from Newton's second law of motion, and the vector version of this law states that if at any time t, a force, this capital F of t, acts on an object of mass m, producing an acceleration a vector of t, then basically Newton's second law becomes, in vector form, becomes, I'll put this like here, the vector f of t equals to mass m, so it's mass like that, times it by a of t, like that, so a vector of t. So yes, that is fascinating stuff. Alright, so now to illustrate this, we're going to actually use an example. We're going to use an example, example 4 on centripetal force. So an object with mass m, that moves in a circular path with constant angular speed omega. This is a w, but in Greek this is a omega symbol. Has position vector r of t equals a times cosine omega t, and then the I plus a sine omega t j vector. All right, and now we're asked find the force acting on the object and show that it is directed towards the origin. So in other words, basically show that the force is always going to be pointing inwards. In other words, we got a centripetal force. All right, so to find the force, we first need to know the acceleration. Because remember, F equals ma is the force acting on the object. So you have the object with mass m and moves in basically this position vector. So we need to find the acceleration of this position vector. And the first thing to do is to find the velocity. So velocity is going to be, v of t is equal to the derivative of the position vector, so r prime of t, and this equals to, take derivative of a cosine omega. A is constant, omega is constant, so what we'll do is derivative of cosine is going to be negative, so negative sine sine omega t, and then using chain rule, derivative of the inside omega t is just going to be omega, or w, like that, yeah. And this is the I vector, and the I component. So that's I, like that. And now the next setup is going to be, well, derivative of a sine omega t. That's just going to be, well, a omega, then sine is going to be just positive cosine t. Omega t, yeah, and then j. So that's j vector. And now we'll take the acceleration. It's going to be the derivative of the velocity. So a of t is equal to the derivative of the velocity, or the second derivative of, or the second derivative of the position vector. So we just put that derivative of the velocity. And now derivative of this one here, sine omega t, well, that's just going to be cosine, and so negative stays there. And then we have to use chain rule, put the w in there, or the omega. So we're going to have, take it out, squared to be cosine omega t, and then I vector, plus, now, well, this one, cosine's going to be negative, sine. So it'll be the same thing, but now we have an omega squared, and then sine omega t, like this. And then this is a j vector. So that is our acceleration. Alright, so therefore, Newton's second law gives the force as, this is just going to be a force of, so F of t is equal to m, so mass, times acceleration. So there's acceleration vector. And now this equals to, well, m. And what I'll actually do is I'll factor out this w squared. Well, I'll keep the a there, and I'll see why, just so that it matches up with this part there. So we'll keep that in there. So we're going to go, I'm going to take the negative omega, and then we're going to have a mass times by omega, so squared, and then times it by a cosine omega t, I, is the I component, and then plus, this is going to be a sine omega t, a j component, like that. Alright, and I just moved it over there. So now note that this part right here, this equals to r of t. So this is just a position vector. So what this means is, that's just this part right here. So that means, so thus, the force is equal to, F of t is equal to negative m omega squared, and then times it by the r vector. So in other words, whatever the, so for, this is just going to be negative of the, with a constant, two constant times it by a position vector. So if the position vector is going this way, then this is just going to be negative of that. So this will be exactly the same, basically exactly the same parallel to it, but it's mean reverse direction. So in other words, it's always going inwards, actually. Yes, it's always going away from this. So if you have a position like this, or r of t, like that, and then, well, if the position vector is like this, so there's the curve, it always goes towards the origin. This is the origin. So, I mean, that's the vector, the position vector that always points towards the origin. That's pretty fascinating stuff. Alright, so going further, so this shows that, and I'll show box this out, this is pretty important. So this shows that the force acts in a direction opposite to the radius vector. This is a radius vector, that's because this is actually a circle. But anyways, this is a position vector, r of t, and therefore points towards the origin. See figure below, I'll illustrate that. So such a force is called a centripetal force, or center-seeking force, and the angular speed of the object moving with position p is omega equals to d theta over dt, where theta is the angle shown below. Alright, so what I'll do now is I'm going to draw a circle. I'll put out a circle right here. Actually, before I get a circle, I just realized this OneNote has this built-in a graph thingy there. So I could move this in there. We have this built in, alright, and now let's put the circle in there. And I'll put the circle, if I hold shift, it makes it a circle. Okay, so we got this. And I'll just move these around, move this over here, get some more, make it a bit bigger. Okay, and now we could even make it even bigger. Alright, this is amazing. Okay, now this is going to save me a lot of, just makes it just much easier now to draw now, because I've had people complaining about my drawings. Okay, now we have perfect drawings, alright? So we got this. Alright, now that we have this, what I'm going to do next is I'm going to draw our position vector. It's going to be like this. And this is going to be our r of t. I'll move it outward like this, r of t. Alright, so that's r of t, and this is the point P, and the reason I'm doing all this is just so we can make sense of this omega, this d theta over dt, and this theta there. Alright, yeah, just fix that up. And now let's say we have an angle theta. So, yeah, that's our angle theta. So, what I'll do now is, I'm going to actually draw our, I'll draw our typical trigonometric setup here, because again, this is just a circled equation of it. So let's say we have that, but now the next step I'm going to draw this in red, actually, to make it easier to see. And now this full length of this position vector, let's say that's A. So let's say this equals to, move it out here, actually. So let's say that just equals to A, and that just equals to the length of the magnitude, or just magnitude of the position vector at time t. All right, so that is what our A is. All right, and if it's A, that means basically that's going to be, well, a constant then. That means that basically the magnitude of this is constant, so you're always going to have just a radius. That's just the radius A. So A is the radius. So, and now you could use our setup here. So this component here is going to be our, well, this is our x, this is our y setup. And again, using basic trigonometry, so we have sine y, and sine theta is equal to opposite over hypotenuse y ray. So this move this A to the other side. What we're going to get this is this equals to, this is going to be equal to A sine theta. And that's the y component. And now this part right here, x is going to equal to, well, cosine theta equals adjacent over hypotenuse, x over A. All right. And then move the A to the other side. So we're going to get A cosine theta. All right. So in other words, where now the position vector now is going to equal to r of t. So it's a function of t. So that means theta has to be a function of t. So in other words, this equals to A cosine theta I component plus, and then this is going to be A sine theta. Sine theta j, like that. All right, here I just moved it over to here. So yeah, basically now this is a function of t, but then we have theta there. So theta has to be a function of t. And basically what the calculus book does is, yeah, it uses this setup here. So basically it has omega equals to the rate change of theta. So that's how we get the theta. And then it also multiplies by t there. So we have this right here. So omega times t. And I'll show you why it does this. So, and now what it does is, so basically where, in our case, the angle theta is equal to, again, this equals to d, the rate change of theta, d over dt times t, where this is just omega, or w, or however it wants to use it. All right, this is going to equal to omega t. Just keep that in mind. So it essentially, we're just making the variable theta slightly, yeah, it has more variables within it. All right, so then that means, well, our r of t position vector is equal to, well, the radius is going to be A. And I'll show you that when I graph it out in GeoGebra. So this is going to be cosine now omega t. So that's the rate change of it, I vector, plus A sine omega t j vector. Alright, going further, and yeah, before we get to the GeoGebra, here's just the figure from my calculus book, and again, it shows you the inwards force there. So everywhere you go, the force is going to be opposite of this vector, so it's always going to be inwards. So this is basically centripetal force, center seeking. And I'll illustrate that with GeoGebra. So let's also graph in the GeoGebra 2D graphing calculator. There's a link to it, and I also add all the variables that are there. So there's A, that's actually just the radius, remember that. Keep that in mind. As you change it, it just gets bigger and bigger. For example, A is 1 here. Actually, this is 1.4 in this graph. So 1.4, and then that's the radius, 1.4. Yeah, that's quite amazing. So A is just the radius, and you can see that as you slide it, it will get bigger and bigger, or smaller and smaller as you move it. Now B, this is just time t. This is t. I put B because we already have the time t variable here, and I'd rather not make this B. I just leave it like that. So because so there's the curve R. And this curve is equal to, well, A cosine omega t, and then A sine omega t. And then this is from negative 10, 10, but this, you can just leave it from 0 to 2 pi. That's all you need. It's just excess because it's going around in a circle. So that is our t, and that curve is this whole thing. That's the curve. So that's what the t is used for in this case. So then a b is, I just move it around. This is going to be the new t. So for example, if you put b for the position vector, I mean for the position p equals to r, where t equals to b. And that's, you get this part right here. So you just plug that inside. All right. So I'll erase these and so on. And okay, now the next setup is omega, and omega is again is rate change of this this theta. So what that means is if you have it equals to 1, well, it just basically it's just going once in a loop. But if you make it equal to 2, that means for every t value, for example, when you get to 2 pi, the full 360 degrees, you actually get 720. So in other words, you do 2 loops around. So again, that governs how fast you go around the circle. And then there's a mass m. It changes the force vector f there. And force, the force vector here is just p. It starts from p, so the point p, to the point p minus m omega squared times p, which is again this part here. And then p is the initial position. This is right here. So where p is the initial position there. Or just so it's graphs it out, that's the r of t. Yeah, so that's going to be the negative, the force there. So basically, it's the vector from here, this starting point, and then subtracting by the force vector. So again, that's how we, and it's always aiming inwards. And again, we'll play this around with it here. So there it is. This is actually quite an amazing setup here. So here is the a and so on, and again, this is from 0 to 2 pi. I made it like that. If you just plug in 2 pi, it automatically goes to 6.283, etc. All right, so there's our equation. I'm going to move it over to this side. Yeah, so now I'm going to zoom in. So now what we have is there's our A. So notice what happens in our A. A is the radius. If I go to 1, the radius is 1. M just affects the force. So because you're just multiplying it by the acceleration. And now this is the omega one. So just keep it at 1. And now here's our B. It goes from 0. There's a 0. That's at time t is 0. And if I go to 360, it makes a full 360 loop. But now let's go back to 0 and change. This is the angular the angular speed, or the angular frequency, or whatever you want to call it. Basically, this angular speed. This is the rate change of theta with time. So let's say we have double the speed. But also notice what happened here. Notice what happens. I'm going to make this 1 here. So let's say we have 1. So 1 becomes like somewhere like that. So let's say we have 2. But remember, this increases the acceleration. Because now this is the rate change of the theta. So in other words, the object's moving faster. So now look at the force. The force is huge now. And now, if I go back to 0, and so it's 0. And now if I go over here, look at the position P. It goes over all the way here. And it goes there. Okay, it goes here. It crosses it once. And if I go again all the way to 360 degree, or pi is 2 radians. 6.2, well, and there it is. So it makes 2 loops because this is 2. So if you have it at 0.5, that means now you actually get half a loop. So from 0 all the way here, you only go here. And look how tiny the force is. So, but if you have a super heavy mass, the force is really big. So this is a heavy mass, super slow angular frequency. It only goes like that. It only goes an arc there. Hey, where's the rest of the thingy there? Oh, that's because it's affected by sine. Okay, so I do need more than this. Okay, never mind. So this is going to be... I need to make this 100. Well, that's on the negative side. So 0. And this is going to be... let's make another 0 there. Just make it... Yeah, so just fill those up. Negative 100, 100. Yeah, because this whole equation, it actually goes to the limits there. Because we have this omega. So yeah, you need more than just 2 pi if you change the angular frequency to be super slow. So basically, that whole idea of it is adds that component. And does it ever make it thicker? I'm not trying to make it thicker. Okay, anyways, I'll just leave it like that. Yeah, so that is that, and that is pretty cool. So again, this is pretty amazing. And then if you make it super fast, and look how giant the force is, because now it's going around the loop super, super fast. Unless you make this, let's say, bigger maybe. I guess you make it super, super giant. Okay, this is super, super giant. I'll make it not as giant because this laptop isn't as powerful as fast. Okay, yeah, but it still doesn't matter. Okay, the mass, yeah, make the mass super tiny. Oh, yeah, if you have a negative, it goes like behind there. But anyways, it's pretty cool. Okay, there's angular frequency, and let's see what happens if I change this mass. Yeah, the force actually, it gets bigger. It gets bigger as you make it bigger because it's the same. Oh yeah, that's because this is the angular with the theta one. But if you have a bigger circle, theta is going to be going. It's going to be going the same speed, but the actual object is going faster. So for example, yeah, it's covering more and more space because this is this circle right here. I mean, this point right here has to go super fast to be the same speed as someone super tiny. Yeah, that's pretty fascinating. So yeah, so notice how it's like super tiny force here because it's going slow, even though the angular speed is the same. And then if you make it bigger, it has to catch up with this little small one, so it's faster there. Anyway, that's pretty fascinating stuff. So play around with that over there. Alright, now let's go further and take a look at example 5, and that's the horizontal distance of a projectile. So a projectile is fired with angle of elevation alpha and initial velocity v0 as in the figure below. So again, there's the initial angle, and it's launching it outward like that. And it's going to go in a parabola setup like that. Alright, and then there's distance d there. So assuming that air resistance is negligible and the only external force is due to gravity, find the position function r of t of the projectile. Alright, and then now we're asked what value of alpha maximizes the range or the horizontal distance traveled. Alright, yeah, so we gotta basically see what's the maximum distance d there for an angle. Like, what angle gives the maximum distance? Alright, so let's go further. So we set up, let's take a look at the solution. So we set up the axes, or the axis, so that the projectile starts at the origin. Again, that's just as in this figure. So we start at the origin there. So since the force due to gravity acts downwards, we have, yeah, what we end up having is, again, it's only force acting on it after you launch it. And that's because air resistance is negligible in this case. So what we'll have is the force due to gravity is going to be F, like that, of t. And this equals to, well, m times acceleration. And that is going to be, well, no, this equals to negative mg. And yeah, that's just negative mg, because acceleration a is just gravity. And it's going to be negative g. So it's aiming downwards, and that is going to be, well, in the y components or the j component. So put that there, in the j component. All right, and then we're going to say where. I'm going to move it over here. So where g. So g is equal to the magnitude of the acceleration of gravity there, and this is approximately equal to 9.8 meters per second, or 9.81 meters per second. Well, let's leave it at 9.8, round that up. So 9.8 meters per second. Yeah, meters per second squared. Yeah, so that's what it is. So basically, it's meters per second. So it's it's basically velocity this is increasing by 9.8 meters per second every second. Yeah, hence why the velocity is increasing. Yeah, so that's basically how you think about it. So if velocity is increasing by 9.8 meters per second every second, so after 2 seconds, it's going to be increasing. It's going to be double the speed and so on. All right, so thus, what we have is, so thus the acceleration is going to equal to, well, just negative g. So just move that m out of there. So we could just cancel these, just get the negative g. So acceleration is just equal to negative g. J, and now again we're asked to find the distance d. In other words, we basically just need the position vector to get this all. So we get the velocity, then we go to then we get to the position. So we just take the integral. All right. So since the derivative of the velocity v of t is equal to a, then let's put we have. So what we have is now, well, the integral. Now we just take the integral of it now. So, so v of t equals to the integral of dt, like that. Yeah, and this equals to, well, integral from, this is going to be negative g. Let's put this in a bracket, actually. Negative g, like that, dt. But also, it's a vector, so we got to put the j component there. Negative gj. Then dt, like that. So this equals to, and now the integral of negative g, that's just going to be, well, negative gt j. Then we have to add a constant. This is going to be plus a constant c, like that. Yeah, where C is just going to equal to, yeah, just equals to V naught at t equals 0. Because you could just put in, V at t equals 0. Because you could just plug in V0 here, and then you're going to get, this is going to vanish, you're just left with C. So that's just equals to, V, I'll call this V naught. And again, this is as I went over earlier, and I basically showed that in general, that's what we have. Whenever we have, in general, if vector integrals allow us to recover velocity when acceleration is known, and it equals like this. So v t naught, the starting position. We just made it at t equals 0. And then this is, and then the position one, when you know velocity, you just go to r t naught, and so on. So, or r naught. This is v naught and r naught, and so on. So it's fascinating stuff. And then plus the integral of that acceleration, and so on. All right, let's continue further. All right, let's go back here. So thus, what we have is v of t is equal to negative g t j. Yeah, j t j, and then plus v naught vector, like that. All right, and now integrating again, we can get the position vector. Yeah, so we're gonna get we're just gonna get I'll just put it like this: r of t now is equal to, well, the integral of the velocity dt, and now this equals to, well, integral from negative tj, and then plus v naught, like that. I'll put a bracket, v naught, like that. This is dt. Now this equals to, well, integral of negative gt. That's going to be, well, gt squared, and then divided by 2. Because you have to, when you, for example, when you take the derivative, put the 2 down, those cancel, and so on. And this is j still. And now plus v naught times t. And now plus d. Like that. Let's put another position vector. I mean the integration constant, and where likewise d right here is just equal to, well, r of 0 there, because we're starting at the origin. We're starting from there, and then put the 0 inside. This all just vanishes, and so on. Yeah, it vanishes, and since we start at the origin, this is just equals to the 0 vector, or the origin. It's just, we just add to nothing. So that's the starting point there. So there it is. So we just have it like that. So we just remove it all. So thus I'll just type it out actually. So thus the position vector of the projectile is given by, and I'll move this a bit higher actually. Move it centered a bit higher. All right. So thus the position vector of the projectile is, and as d just vanishes, so we get a r of t, because now we need to maximize this value. That's basically the just the full length of it. Well, actually, we need to maximize the horizontal distance of it, and we're going to break that into components. So what we'll do is I'm going to write this down. So negative gt squared over, I'll put it over 2j, and now plus v over, the calculus book puts a t in front, so t, then v vector naught, like that. So that's what we have. So that's a position vector. All right. Well, actually, I'm not going to bold this one, because this isn't the final thing. We need to maximize the distance. That's the thing. That's the key part. So let's keep going further. All right, going further. So now if we write that the magnitude of the initial velocity vector is equal to just v naught, not like that, so not a vector. It's a scalar. Just put it like that. Just put the italics v there. The initial speed of the projectile. Then what we have is, well, if we look at our setup here, I'm going to write this out like this. So we have our x, this is our y. So we have vector. This is our starting vector here. This is our alpha. All right, and now we're going to get, this is our v naught. So this is our v equals to v naught, like that. Oh, whoops. Actually, I'm just going to put v naught, yeah. So we already wrote it over here. So we already wrote it there. So that's our v naught. Like that, that's the length, and this is going to be our vector of v, not like vector, like that. And now this is draw our typical trigonomic triangle as always. All right, just fix that up so we have it like this. So what we get now is what I'll call this. I'm going to call this v not the y component. And now this part here, again, there's the origin. All right, and now this, the adjacent side, I'm going to make this VOX, or V naught x. All right, so again, using basic trigonometry, what we have as well, we know sine alpha is equal to, well, it's going to be opposite V naught y component over the hypotenuse, which is just the magnitude, the V naught. Like that. And then move it over to the other side like that. This is going to equal to V naught sine alpha. All right, and then likewise cosine of alpha is equal to adjacent over that. So V naught x over V naught, move this over to the other side. What we get now, this equals to V naught, just the magnitude of that initial velocity. V naught, and then times it by cosine. Cosine, and then this is going to be alpha. And here I quickly just fix this up, and I added this just for completeness. So V naught, the magnitude vector of that equals to V naught. Yeah, so V naught vector there. All right, so thus what we get is V naught is equal to, yeah, so we're going to put this in its components. Yeah, just because we have this right here. So we're going to put this in its components. So this is going to equal to V naught cosine alpha I plus V naught. And then this is going to be sine alpha. And then this is going to be our J vector, like that. Alright, so thus the position vector of the projectile becomes, so we have this whole setup here. I'll just copy this. So instead of writing it down again, I'll copy this and paste it in here. So this becomes now, we just plug in this V naught inside there. So we plug in this whole thing inside here. Alright, so we're going to get this equals to, well, this one has an I component, and this one doesn't have an I component, it's just a J. So that means we're going to have this part here. So we're going to have this right here, the I component. I'm going to write this out. I'll put in a bracket. So V naught cosine alpha, but then we're going to multiply by t. So multiply by t. So you put the bracket so it doesn't look like it's alpha t inside there. Now we have the I component. And now plus, now the next one is going to be, well, this is going to be inside here. So what that will look like is this. This will look like all two brackets. It's going to be like a bracket. Yeah, square bracket and then a regular bracket. This is going to be now, we're going to have this as the positive one. I'll put the negative on the right. So V naught sine theta. V naught sine alpha. And then times it by t, because we're multiplying this inside here, this t. And now we're going to have subtracted by gt squared. Gt, squared over 2. Yeah, and this is going to be a closed bracket. And this is our J vector, like that. Alright, so now that we have this, the next setup is, well, we can have now our parametric equations of the trajectory are therefore, and basically take the x and y components. So this is the x1, so the x component is equal to, just the I setup there. So this is going to be now equals to V naught cosine alpha times t. And then the y component is going to be equal to V naught sine alpha times t minus gt squared over 2, like that. Alright, now we have all this. Now this is what we box in, because this is pretty much what we can start to obtain distance. Because we want to get the maximum distance, horizontal distance traveled for basically the alpha, which alpha gives the highest, the farthest distance. So what value maximizes the range of horizontal distance travels? Basically maximizes d. So that we need to find the perfect angle. It should be 45 degrees. That's my guess. All right, and now just a quick note here, just a side quest here. So if you eliminate t from the above equations, you'll see that y is a quadratic function of x. So the path of the projectile is part of a parabola. So for example, if I just take this right here and then move it over to over there, so we have t as a function of x. So what we get is t equals to x over v naught cosine alpha. And now we throw this inside the y there. So what we get here is we get y is equal to, well, we got a v naught. Yeah, we just throw the t inside there. So I'm going to put this like this. We have this v naught sine alpha, then times by t. Now it's going to be times by x over v naught. This is cosine alpha, like that. Yeah, here, just fix that up. I put the alpha at the bottom there. Yeah, so that's the alpha. Let's make it. It's hard to write alpha. All right, we'll do one more time. All right, so there's alpha, and then yeah, so v naught sine alpha divided by v naught cosine alpha, and then minus, this is going to be, well, g, and now the t is going to be this setup here. So g x squared over, well, there's a 2 here, so it's going to be over 2 v naught squared cosine alpha squared, like that. Yeah, so in other words, well, this cancels, and then we're gonna get the top part's gonna be, well, tan alpha. So just cancel like that to make it thinner so we can see it. So this equals 2. So yeah, we get y is equal to tan alpha x, and then minus, again, this whole setup there. So g x squared over, I'll put it over here. And here, let's move it over, actually, erase that, move it here, put this in a bracket so it doesn't look like it's part of the tan. And then minus, move that all these giant constants by itself. So g2v naught squared cosine alpha squared, and then times it by x squared. All right, so yeah, so this is just a quadratic formula. This is just a problem. I'll just put this like this. I'm not going to graph this out because we need all the other variables and so on. But it's just a parabola because it's just there's the x squared, there's an x, and you just manipulate that, and everything else is the constant. So it's just a parabola. All right. So continuing further, and again, this parabola, whenever you have an x squared, x, or just everything else is constants. You just get a parabola when the highest power is x squared. All right. So going further, so the horizontal distance d is the value of x when y is equal to 0. Yeah, so basically, we have the parabola. So it's basically parabola, so we have the starting point y equals 0. So basically, when y hits the 0 again, that's going to be the distance d. So at that x value. So let's continue further. So setting y equals 0, we obtain, yeah, so what we obtain, well, we're going to get a t value, and then we're going to throw that inside the x one. So we have this right here. So y equals to this whole setup there. So y equals to v naught sine alpha t. Yes, let's go back up here. So, and then sine alpha t minus gt squared. Minus gt squared over 2, like that. And now set this equal to 0. So that's when it's equal to 0. So now, and then we can basically cancel out one of the t's, or instead of that, I'll just factor it out. So what we're going to get is we're going to get a t, and then, yeah, so that's t times it by, then we have a v naught sine alpha minus gt over 2. This equals to 0. So we have two setups. We have at the origin, this is at equals 0, at t equals to 0. Equals 0, or this whole setup is, yeah, I'll just put it like this. So we have this, this can equal 0, or this whole thing can equal 0, so that this whole thing becomes 0. All right? Yeah, so thus what we have is, thus, t is equal to 0, or, that's at the origin, that's a trivial one, or we have, or when then, if this is equal to 0, so then these two are equal to each other, or this equals to the negative. This one, yeah, move it over to the other side so they're equal to each other. So we're going to get a, yeah, we're basically set it equal to each other and then move these over to the other side. So what we get is, g. Yeah, so what we get is equals to t is equal to, move this over to the other side, v naught sine alpha, and then move the 2 on the other side, so 2 times it by that, and then divided by g, like that. All right, so I'm going to box these in, and yeah, those are the answers for t. Now we just plug that into our x value, and we'll find the maximum. All right, so now this second value of t gives, and now we'll plug it in. So d is then equal to the distance, is equal to, well, just the x component. and then that is going to be equal to, where's the parametric equation? V naught cosine alpha, then times it by t. So V naught, yeah, write it down here, V naught. All right, and then cosine alpha, and then t. I'll put the whole thing in. Yeah, so again, that's V naught cosine alpha t, and then throw this whole thing inside there. All right, so throw that inside. All right, what we're going to get is this equals to a V naught cosine alpha, and then times it by, I'll put a bracket, times it by 2 V naught sine alpha, divided by g. And then simplifying this, well, this equals 2, and then the v will have a 2v, I'll put the v naught squared first. So v naught squared, those ones squared, divided by g, and then we're going to have a multiplication here, times by 2 sine alpha cosine alpha. So this is going to be a 2 sine, and the reason I put it like this is because this is just, we already know the identity for this. This is going to be sine alpha, and then cosine alpha, and the identity, which I covered, proved in my earlier video, put the alpha like this. This right here equals to just sine 2 alpha. Yeah, that's what it equals. Yeah, and I'll link back to my earlier video on that. Basically, now this whole thing becomes now, well, d is equal to x, and that equals to v naught, I'll put it like this, v naught squared sine 2 alpha divided by g. And that is our distance formula. And now we need to know when it's maximum, and that's going to be, yeah, it's going to be when sine 2 alpha is maximum. In other words, typically it's you'll have pi over 2, but there's a 2 there, so divide by 2, it's going to be pi over 4, and I'll show you that in a bit. But first, recall the sine double angle identity from my earlier video, and then I just took a screenshot from my calculus book. So this is the double angle sine 2x equals to 2 sine x, and there's the other ones for cosine, and there's and then tan for tangent as well. And this one has multiple ones, and so on. Like that, you can end this one here. Anyways, so you can see a link to my earlier video to proof on this one. Or let's go further. So clearly D has its maximum value when sine 2 alpha is equal to 1. That is when alpha is equal to pi over 4 radians. All right, and you can see that because, again, it's a sine function, so this is the only thing we have here. So this one's the constant squared, and then the g is a constant. So the only thing that changes is the sine 2 alpha. So just recall the graph for sine theta. Yeah, just fix that up. So that's theta, and there's sine theta. So then it looks like this, and goes up and down, and so on. I'll fix this up a bit, like that. All right, now here's the origin, and then at here is 1. And then here's -1, and then at here is going to be pi over 2. That's a maximum there, but that is when theta is equal to pi over 2. Yeah, or better yet, I just move it over there, and I'll just say maximum at theta equals pi over 2. So that's the maximum at theta equals pi over 2. Where in this case theta, because we have sine theta, it's going to be sine 2 alpha. So it's going to be, well, equals to 2 alpha. Whoops, this is going to be like that. So in other words, move this over, we get alpha is equal to pi over 4. All right, now that we have this, yeah, we can go on to the next example. So example 6, impact speed of projectile, and this is also going to be hitting the ground. So a projectile is fired with muzzle speed 150 meters per second and angle of elevation 45. Yeah, 45 degrees. You forgot to add that degree symbol there. So 45 degrees from a position 10 meters above ground level. And now we're asked, where does the projectile hit the ground and with what speed? Alright, so it's basically the same thing as the previous example, but the only difference is now that it's being launched from a height above the ground, so 10 meters above, but you're just being launched by it from an angle and so on. So solution, if we place the origin at ground level and then the initial position of the projectile has coordinates 0.10. So it's it's 10 meters above the origin. And so we need to adjust the earlier parametric equations of trajectory by adding 10 to the expression for y. All right, and I'll go over that as we solve this. So with, let's write down what we're given. So with, we have v naught is this initial speed. So it's the muzzle speed. So v naught is equal to 150 meters per second. All right, and now we have alpha. So alpha is equal to 45 degrees, like that. And this just equals to, well, we know this is just going to be pi. That's just, pi over, that's 90 degrees divided by 2. So this is just pi over 4, or in other words, pi over 2 divided by 2. So pi over 4 radians. I'll put this better. Radians, all right? And we also know that, well, we're going to assume g is equal to 9.8 meters per second, or approximately equal to, just fix that approximately sign, or just equal to, doesn't matter, it's all close enough. So 9.8 meters per second squared, so 9.8 meters per second per second. All right, and now let's draw. And actually, I'm just going to ignore this with part. We don't need to write that. I was going to, because Calculus book says with this, then we have, I'm going to move this over here, and I'll fix everything up. Yeah, all right, here, I just moved everything over there. So now let's just draw this out, how it looks like, the trajectory. So let's say we have the y-axis, and now we're going to have the x-axis. There, and there's the origin, and then there's the height, 10 meters. So there's the 10 meters. I'll put the 10 better. All right. 10 meters. All right, so that's 10 meters, and it's going to be launching from like this. And that is our initial launch there, and I'll call this, and it has a v naught velocity, like that, and then there's going to be an angle alpha. Yeah, an angle alpha, like that, and that equals to 45 degrees. Or pi over 4. So that's just, I'll just put alpha like that. All right, so that's the launch, and now it's going to basically go in a parabola. It's going to go like this, and then launch all the way down here. So I'm going to move this, actually. It's going to be like that, and I'll put it like that. Yeah, I'll just make it like this. Yeah, I'll put it above here. Let's say initially it's like a straight line, and then it's going to go land right over here, and that is the distance we want. So it's going to land there, and now we want a distance d, and that's what we're asked. Where does the projectile hit the ground, and with what speed? So what's the speed that it hits the ground with? And then we can go v final there. All right, so let's take a look now at our equations of the parametric equations of trajectory as I covered earlier. So we have these. So we have, this is the equations. So this is x. What I'll do is I'll copy. Yeah, let's copy this whole thing here. So this is what we derived before, and then for the y, because initially we started at the origin, we just need to add that extra height. So there is our setup there. Yeah, so that is x equals to v naught cosine alpha then times t. Then this y is equal to v naught sine alpha times t minus gt squared over 2. But now we need to add a plus 10 because initially it was starting at the origin. Now we just add an extra 10 meters so that the initial height's there. So when you plug in 0 for time t, the height goes to here. All right, so it goes like that. And now for the x one, well, we know x is going to equal to, v naught is equal to 150 meters per second. 150 meters per second. I'll just leave it like that. And then cosine alpha, cosine pi over 4, then times t. All right, so this is what we have for the x. And we need to solve for x, but there's a t there. So we need to know what t is. And we can solve for t by, well, setting y equals 0 here. So at here, we have y equals 0. This is with the impact. So then we just set this equal to 0 and solve for t, and then throw this in there, and then we solve for x. All right, so what we'll do, again, is similar to the other setup. So we're going to write y is equal to v naught. Actually, I'll put it all over here, actually. Let's... Yeah, I'll just put it all here. We're going to have to do some quadratic formula setup, but still, we can just put it all in here. So y equals to v naught is 150 meters per second, and then times by sine alpha, which is, again, pi over 4, because typically, dealing with radians is easier, because all the calculators default is radians. All right, so that's what we have, times by t, and then minus 9.8 divided by 2. I'll just put that in for completeness. 9.8 divided by 2 t squared, then plus t. I'm plus 10. All right, now what we could do is, what I'll do is, well, if you notice here, this sine pi over 4, we could get the exact trig ratio of this. So what we'll do is recall. All right, recall. So if we just have a triangle set up, I'll actually put it out here. Actually, what I'll do is also put it here as well. So this as well, recall that what we're going to get is, if we were to draw a square, I did a video on this, but I like doing this always, just instead of remembering it, just do it. Okay, so we have this is just a square, and its lengths are 1, 1, 1, 1. And so then the angle in between across like this is going to be, well, 45 degrees. So that's 45 degrees. In other words, yeah, this is 45. Or in radians, it's going to be pi over 4. Yeah, so then this one here, using Pythagoras, this is 1 squared plus 1 squared. This equals to, well, just 2 here. This is square root 2. So that's just square root 2. So yeah, just 1 squared plus 1 squared, not all square root. That's Pythagoras theorem. So then this means now, well, sine of pi over 4 is equal to opposite over adjacent. Opposite over hypotenuse, so 1 over square root 2. So that's what it is. But also, calculus book always puts the square root on the top, so I'm going to multiply it square root on top and bottom. So not changing anything. So what we're going to get is, well, this square root 2 times square root 2, that just equals to 2 there. So we're going to get equals to square root 2 over 2. All right, so that's what it equals to. And likewise, cosine pi over 4, this equals 2, well, it's going to equal to, again, adjacent of our hypotenuse, so 1 over square root 2, and that also equals to square root 2 over 2. So they're both exactly the same thing. All right, so thus what we have is, well, the x1 is going to be, thus, x is equal to, well, 150 times by square root 2 over 2. That's just going to be 150, divided by 2 is 75. So this is just going to be 75 square root 2 times t. All right, and then the other one's going to be y is going to equal to, I'll box both of them separately because we're going to have to do this, put the quadratic formula on the other one. Right here, I just fix that box up. So this is going to be y. Yeah, this one, fix that up. So y is going to be, well, 150 divided by 2 is just going to be, well, 75. And then sine, yeah, that's a square root 2. So we're going to have 75 square root 2 t minus 9.8 over 2. Yeah, minus 9.8 over 2. That's just 4.9. So again, 9.8 divided by 2. This 2 goes into 9. Well, it's like, think of it, imagine it was 100. 100 divided by 2 is 50, but there's a 98. So 98 divided by 2 is going to be, 49. Yeah, and then put the dot there, so 4.9. All right, so 4.9 t squared, and then plus 10. All right, so going further, so now impact of the ground occurs when y equals 0, as I drew over there. So which we can solve via the quadratic formula from my earlier video, and using only the positive value of t we get. So here's a recall from my earlier video, there's a link to it, and there it is, the proof. I basically use to complete the square. So ax squared plus bx plus c equals 0, and then when you set that equals 0, set this one equal to 0, and then basically if you complete the square by noting that x plus d and then all squared, if you FOIL this out, x squared plus 2dx plus d squared. And then basically you do the same thing with this one here. So you divide a out. So you're going to have a c divided by a, b divided by a, and so on. And then we're going to have to plus and minus b, something like that. Yeah, we're going to have to actually, actually, if I recall, it's going to be b over a. So we're going to have to do something plus and minus something to get this set up, so that we can just put it in here. So x plus b over 2a and so on. Anyways, you can go and figure that out and watch a video for that. But anyways, here's a quadratic formula. X equals to negative b plus or minus squared b squared minus 4ac divided by 2a. All right. So in our case, I'm going to rearrange this so that it lines up with this x squared with x squared x and then the constant on the other side, with the 10 on the end. So we're going to have, so I'll write thus, we have y is equal to, and I'll put this negative 4.9, negative 4.9 t squared right here. And then this is going to be plus 75 plus 75 times square root 2. Oops. Square root 2. Square root 2 t, and then plus 10. And then set this equal to 0. So this equals to 0. Alright. Let's fix this up. I keep writing it softly for some reason. Alright. Yes, equals 0. So now this one's going to be our A, this is our B, and this is our C. Yeah, so we're going to have, instead of x here, our variable is t. So we're going to have t is equal to, well, negative b, which is going to be 75 times it by square root 2, and then plus or minus, and now we have a plus or minus, and then this is going to be, well, square root b, this is going to be b squared, b squared is going to be, well, 75 squared, and then square root 2 squared is going to be 2, alright, and now, make this thicker, I don't know why it's always so thin, alright, and now this is going to be minus 4a, so a is going to be negative 4.9, so if it's negative minus negative there, it's going to be, well, positive. So it's going to be 4 times it by 4.9, and then times it by c, where c is going to be 10 times by 10, like that. Alright, extend it over there, extend it even further like this. Alright, that's what we have, and then we have to divide by, well, 2a, so 2 times it by a, which is negative 4.9. So I'll put a negative out there, 4.9, like that. So that's what we have. And now what we have is, well, we have a negative on top. There's negative here, but there's also plus, minus. So just divide out the negatives. Just be plus. But then this one, if it was plus, minus, now it becomes minus, plus. So if it was minus, it becomes plus. If it was plus, it becomes minus. But in fact, this is actually bigger than this number. So we're going to get a negative number. So we're only going to look at the positive values. So we only want positive values of t. So what we end up having is, well, this equals to, just simplify it even further, 75 times square root 2 plus, and then calculus book just calculates this out. 75 squared times 2 is actually going to equal to 11,250. Yeah, so 11,250 plus 4 times 4.9 times 10, that's going to be 4 times 49. It's actually going to be 196. And I'll do a calculation check soon with my built-in OneNote calculator. 196, like that. And I'm going to extend this. Alright, extend that. And now divided by 2 times 4.9, that's just 9.8. Alright, and now this, plugging this in the calculator, we're going to get a approximately equals to 21.74, and it's actually going to be seconds, just because we were dealing with gravity is 9.8 meters per second squared, so we had the seconds, and then we had the 100. The speed was 150 meters per second initially, so yeah, it's going to get cancelled out somehow, get s there. Alright, so thus, or then, so we have that, then our x value, x, or is it going to be now d, actually? So d is equal to x equals to, basically this is going to be d equals x, and that is going to be, well, we have this, x is 75 times square root 2 times by t now. So this is going to be 75 times square root 2 times by t, and now we just throw this inside. So this is going to equal to 75, or approximately now, because that's an approximation. Approximately 75. Yes, erase this. 75 times square root 2 times it by 21.74. Alright, now if you plug this in the calculator, what we're going to get is approximately equals to 2,306 meters. So at 150 meters per second, meters per second velocity, that you're launching something at 45 degrees, you're going to get basically, it's going to be in the air for 21 seconds and land in, it's going to go 2,300 meters. Holy, so 2,306 meters approximately. Alright, yeah, so basically, the projectile hits the ground about 2,306 meters away, and just a quick calculation check, so we have 75 squared, 75 squared times 2, that's this part right here. Just put in the OneNote calculator, just erase this, put equal space, and it goes there, 11250, so that's this one here, and now this one, 4 times 4.9 times 10, so 4 times 4.9 times 10, that's just, 196, again, you could press space. And then 250 plus 196 equals 11,446. Yeah, I just put that there, and then the reason is just if you squared 11,446, that's this part right here, we're gonna get a 106.98. But then if we have this 75 times square root 2, we get this 106.066. It's interesting, so it's a bit off. I'm not sure why. I think it's because. Yeah, actually, I think it's because it's 4.9. That's gravity. That's it's more of an approximation because this one just 75 times square root 2. So that's an interesting setup there. Yeah, I'm not sure exactly why that's different. But then, but anyways, so if you made the negative there, these would pretty much cancel out. But yeah, I'm not sure what the rounding errors, or it might be just the calculator, the calculator, the way it does square roots, it might be different than square root 11,446, etc. So whatever reason is, but in theory it should be cancel out. So the exact one, these should cancel out. So if you have a minus, you get t equals to 0. So in other words, we just ignore the negative sign, we just do the positive. Yeah, I just wanted to double check that, so to see what happens. And now if you go 75 times square root 2 right here, times it by this square root 11,446. That's add these up, and then divided by 9.8. So divide by 9.8. This is gonna be 21.74, and this is gonna be 21. Yeah, that's it. Space. So that's it. Yeah, so that's it. And then finally, we have this one here, the distance. D equals x. Basically 75 times square root 2 times 21.74. So 75 times square root 2 times 21.74, that equals to this whole giant thingy, space. So 2305.875, like that. Oh, and then just round this up, 2306 meters. So yes, fascinating stuff there. Alright, and now the next part of the question, that's actually on the velocity of the projectile. Because remember, we're asked to find the distance it goes. So basically, we're asked where does a projectile hit the ground, and with what speed. So we need to find the actual speed hitting the ground. And again, so we have the distance right here. That's about 2,306 meters. Now we need to know the velocity. Well, we know the velocity. The velocity of the projectile is it's just a derivative of the position vector. But first, note, or I'll just say we have. Yeah, so the position vector is going to be r of t, and this equals to, well, we have the parametric equations of it. That's this part right here. These two are the parametric equations, so let's just put those in their I and j format. So 75 square root 2 is going to be like this. So it's going to be 75 square root 2 times t, and it's going to be I, like that. And then the next one's going to be plus. And then plus, this one is 75 square root 2 t minus 4.9 t squared plus 10. So we're going to get a plus 75 square root 2 t squared. And then this is going to be, yeah, now we need to put a bracket actually. And then the next one's going to be minus 4.9. Oh, no, this is not t squared. This is just t. That's just t. Let's go back up. That's just t, and then 4.9 t squared plus 10. All right, so this is going to be 4.9 t squared plus 10. And this is going to be our j component. And this is going to be bracket j, like that. All right, so we have that. Yeah, so I moved it over here. So thus, the velocity vector, v of t, is equal to, well, the derivative of the position vector, r prime of t. So now this equals to, let's just take the derivative, this t, this just becomes just a constant. So we're going to have a 75 square root 2, that's it, I. And now this one here, well, the derivative of 10 is going to be 0. This one here is going to be, well, the t just vanishes, so we're going to have plus 75 square root 2, and then, yeah, the t is gone. Next one's going to be 4.9 times 2, that's going to be 9.8 times t. And then j. Right, so that's what we have, and yeah, that's the velocity vector. So its speed at impact is, well, at t is equal to, well, 21.74. So at that. So, and then we need to get the magnitude of that. So the speed is is basically the length of it, or the magnitude of it. So thus its speed at impact is going to be this absolute value sign. So of t at, well, 21.74. That's what t equals 21.74. Seconds, so it's going to be like that. So then the length of it, and then this one again is just the 3D distance formula, or 2D, doesn't matter. And now this is going to be square root, and then we have to square root square the components. So 75 squared, it's going to be, well, 75. I'll just put it like this. Yeah, the calculus book just puts it all like this now. 75 square root 2 squared, and then plus now this whole other setup here. There, so we're going to have a 75 square root 2 minus 9.8 times, and then 21.74 times 21.74, and then all squared, like that. Yeah, so that's the dot. Make it higher so it's not, doesn't look like the decimal place. So that's it. Now right here, just moved it over. Now we just extend this over like that. Okay, so that's what we have. And now if you plug this into the calculator, it's going to be roughly equal to, well, 151 meters per second. Yeah, this is going to be meters per second, like that. So that's the velocity upon impact. All right, yeah, that's what we have, 151 meters per second. And lastly, let's do a calculation check. So here's again with my built-in OneNote calculator. Yeah, I can just write square root and then have 7, and then put a bracket, 75 times square root 2, and then square this side, and then 75 times square root 2 minus 9.8 times 2.1 times 21.74, and then square root that, and then put the bracket at the end. Again, I just press equals space, and I get that all the way. So yeah, 150.65 rounded up to 151. So yeah, good enough. All right, so that's absolutely fascinating. All right, and now let's go to the last section of this pretty epic long video, and that's going to be on tangential and normal components of acceleration. And also note that I just quickly Google searched and the pronunciation of this tangential. But apparently it's pronounced tangential. So tangential, it's not tangential, but I've been always calling it tangential this time. So I'll use whatever floats my boat. So and comment below how you pronounce this. So again, tangential is what I've been pronouncing it, but apparently it's tangential. Okay, anyways, so when we study the motion of a particle, it is often useful to resolve the acceleration into two components, one in the direction of the tangent and the other in the direction of the normal. So first, recall the unit tangent, unit normal, and unit binormal vectors from my earlier video. So here's the one I went over. So the unit tangent, and again, it says unit is because all these are length 1, because you're taking the vector and you're just dividing it by its magnitude. So then basically it's always going to be the length 1. Well, when you find the magnitude of this, always 1, because you're dividing this vector by it, and then just so happens that when you do that, it's always going to be length 1. So all these are length 1. They're all unit. That's why it's called unit. All right, and then there's the binormal. This is the normal one. So anyways, so the tangent one, the t, is basically in the direction of the velocity. This is the derivative of the position vector, and then divide by its magnitude. So t is like that. And then the unit normal is going to be, well, we take this one here and then divide it, the derivative of this one. This is the unit normal one, actually. This is the unit normal. The normal one is here, the derivative of this t, and then it ends up going downwards like that. It's pretty interesting. Like that, and they're all right at angles to each other. So again, watch my earlier video on that. And then there's the, this one is just the, derivative of the unit tangent divided by its magnitude. And then unit binormal is this setup here. Yeah, so unit is just to take the cross product of these two. So cross product, and then you're going to get a perpendicular vector here. So let's take cross product of the unit tangent, unit normal vectors. Anyways, so you could see that video to learn more. All right, so if we write now, v, just put in italics like that, equals to the magnitude of the velocity and then so we're going to denote this for the speed of the particle, as I've done in my just earlier examples above. Then the unit tangent vector is, yeah, so if we write this down, so we have the unit tangent vector is this setup. So what we have is, well, unit tangent vector of t, this is a capital T of lowercase t, equals to the derivative of the position vector, so this is tangent vector, divided by the magnitude of it, of the position vector, derivative of the position vector. And now remember, velocity is just the derivative of the position vector. So this is just a velocity vector. So this just equals to velocity, like that, of t, divided by, now this is just going to be divided by the magnitude of this position vector derivative, in other words, the magnitude of the velocity vector. Let's put it like that. All right, like that. And now this equals to, well, this one is just our lowercase v. I mean just our italics v there. So this just equals to, yeah, it's a v velocity vector divided by v, the speed. And now what we could do is, well, we could just move this over. Yes, move this over to the other side. So what we get, and so we get the velocity vector of t is equal to the speed of the particle times it by its unit tangent vector. So it's pretty great stuff there. And this is expected because, again, this isn't the velocity is going in the direction of the particle motion, and that's just the derivative of the position vector, which is just a tangent vector. And then basically we take a unit tangent of it, just to get the vector in direction of with the length 1, and then just multiply by the full speed. The full speed is going to be, let's say, this much. So it just means it's pointing in this much. The vector is going to be just extended. So all you're doing is multiplying it out. So yeah, it's pretty straightforward stuff. All right, and now if we differentiate both sides of this equation with respect to t, we get acceleration. Well, we're going to get the acceleration, the a vector is equal to the derivative of the velocity vector. So now this equals to, well, this is just the speed of it. Well, the speed is going to be varying depending on whatever the magnitude of the velocity vector is at that time t. So this is going to be using just product rule. It's going to be derivative of v prime. Yeah, it's the derivative of the velocity. Of the speed, and then times it by the times it by t like that. Let's put t like that separate. Yeah, I'll just ignore that lowercase. See, now plus again using product rule, and now this is going to be now v, the speed, times it by the derivative of the tangent vector is just going to be t prime like that. All right, so that's what we have. Yeah, I'm actually going to box this out. So this is our speed. I mean, this is acceleration. This is pretty interesting. So that's acceleration in terms of the tangent vector, and it's also its derivative. All right, so now going further. So if we use the expression for the curvature given by my earlier video on curvature, then we have also we need to do this. Yeah, given by my earlier video again on curvatures. It's just given. Then we have, so here's again a recall from my earlier videos, link to it. And again, there's a link to the notes, and then if you scroll all the way to the bottom, you get all the thumbnails for these sections playlist. So there's the arc length, and there is the curvature. So if we have the arc length like this. Yeah, this is the arc length. There's the s value there, and remember the s is just going to be the integral of, just the integral of a tangent vector there, and then I show that it's equals to this giant thingy there. Yeah, basically these are just think about it, just the 3D distance formula and so on, and what it ends up being is, and then basically the derivative of this is just equal to the integrand part there. So again, just using fundamental theorem of calculus. So ds over dt equals to this. And then what I showed is, again, this the key part that I'm interested in is this formula over here. Again, this arc length is just secondary, but there's the equation for curvature. So we have the tangent unit tangent vector, and then I show that the curvature is this setup here. So curvature, this is a kappa symbol, and then kappa of t equals to the derivative, the magnitude of the derivative of the unit tangent vector divided by the unit tangent, divided by the magnitude of the tangent vector, or the derivative of the position vector. Anyways, so that's that. And also I just did a quick recap on the arc length. But again, watch the videos. It's pretty extensive and so on. So there's curvature, and this is basic curvature is defined as d. This is the derivative of the unit tangent vector with respect to the arc length. So that's why instead of dt, do that. But then if I rearrange it in terms of t, you get this setup here. All right, and we'll deal with this other one later. But anyways, so that's what we have. All right, so thus, in our case, we're gonna have kappa of so kappa is gonna equal to the magnitude of the unit tangent vector derivative, like that. This part right here. Just put that over here. Yes, that's what we're looking at. And then divided by the magnitude of the position derivative of the position vector. In other words, that's just tangent vector. All right, so that like that. And now this equals to, well, what do we have here? This right here, that is just this part here. This just equals to the magnitude of velocity. In other words, that's just the speed. So that just equals to v. So this equals to, this equals to the derivative of the unit tangent vector magnitude divided by the speed. And again, that's what we have. So then we move this over to the other side. So then we have a value for this this part right here, and that's going to be this part here. Well, we're going to have a setup there. Well, actually, that's the magnitude. This is just normal, but then we'll use the other normal vector setup. But anyways, so we have that. I'm going to move this over to the other side. So what we're going to get is that the magnitude of the unit tangent vector is equal to the kappa times it by the speed. All right, so that's what we have, and I will box this in, or I'll put I'll just move it over there, and instead of putting an arrow, I'll put so, because the calculus book does that. So we have this, and this is going to be kappa times v there for the speed. All right, so now what this all means is, we can go further. So now the unit normal vector was defined as capital N equals to, this is the unit tangent vector derivative divided by the magnitude of the unit tangent vector derivative. And again, that's over here. This is the unit normal. So we'll take this one right here. And again, we have this, and then we have this one in terms of kappa v. So again, that's why we want this normal there. So that because we're going to write the acceleration in terms of normal and tangent vector, but then we have this thing here. So we got to get rid of this derivative there. And that's what we're going to reuse the normal vector. So we have capital N vector. This equals to, so this equals to, I'll just write it out fully, just like that. Derivative of the unit tangent vector divided by the magnitude of the unit tangent vector derivative. And so that's what we have. And we also have, so then basically we have that. So then we can just rearrange this thingy there. Or just plug that in. So we have this right here. This equals to unit tangent vector derivative divided by, this is going to be, just throw this in there. Just throw that in there. So we just throw that in there. So we're going to throw that in there and see what happens. So this is going to be kappa v. And now we're going to move this over to the other side. So what we get is so I'll put let's put it like this. Just arrow. Arrow's good enough. Yes, we throw that. We throw it over to the end side. Throw it in there, and then so thus, we'll just leave it like that. So this is going to be unit tangent vector derivative is equal to kappa times velocity, the speed, times it by the normal unit tangent vector, or the unit normal vector. So that is what we have there. Yeah, so that is pretty epic. I'll erase this and fit this bit nicer. All right, and then box this in. Yeah, so now we could throw that in here. And then we're going to have the acceleration in terms of the unit tangent vector and the unit normal vector. All right, yeah, so let's put that in here. So thus, the acceleration, so again, I'll just put the acceleration first, the full thing we had here. Thus, acceleration, this equals to v, the derivative of the speed, so v prime, and then times it by unit tangent vector, and then plus the speed times it by the derivative of the unit tangent vector, plus the this one just v, the speed, times by unit tangent vector derivative. So in other words, this equals to, and now we throw this inside here. Yeah, so this is going to equal to v prime t plus v. Yeah, there's going to be v squared. There's going to be kappa. I'll put the kappa better. Kappa v squared, and then this is going to be the normal vector. So we wrote the acceleration in terms of the unit tangent and unit normal vectors, which is quite astonishing if you think about it. All right, now going further. So now if we write a subscript capital T and a subscript capital N for the tangential and normal components of acceleration, what we end up having is we get a is equal to a tangential. Yeah, and that's just this velocity and the speed derivative. So that's going to be a tangential times by t tangent, the unit tangent vector, plus now we have this is going to be a normal, an, and this is going to be normal like that times by unit normal vector there. Where, and I'll just write this here, where should I write this? I think where a subscript t is equal to just the speed, the derivative of the speed, and an capital a subscript capital N is equal to kappa, the curvature, times by the speed squared. All right, so yes, that's pretty fascinating. I'm going to put this in the center. Let's write this like this and put this in the center. Just fascinating stuff there. So that's pretty epic. All right, now going further, let's draw this out. So this resolution is illustrated in the figure below. So let's say we had a curve. The position is like this. Let's say it looks like that. Yeah, something like that. Or make it a bit, more like this. All right, so it looks like that. So now let's say we have, at this point here, we're going to have a tangent vector. So this is going to be our tangent vector. What I'll draw is actually, I'll just leave it like this. So that this is going to be our tangent vector, t prime like that. And let's say we have the acceleration is somewhere like this. It's accelerating this way, and it has a big acceleration vector like that. There, and now it has a unit normal vector. So it has a unit normal vector like this. This is going to be n. But remember, these are all length 1, so you have to keep that in mind. So this right here is length 1. It's a unit it's a unit tangent vector. This is a unit normal vector. This is going to be length 1. 1 like that. So these are all length 1. And now, like there. So now what I'm going to do is, this is the vector, or this is the acceleration vector, but now if you draw its components, it's going to be relative to the normal and the tangent. This is why it's pretty useful. So this extend all the way across like that. So now this part right here, this full magnitude, is going to be equal to a t. That's just the v speed derivative. And now this setup here, the horizontal or the one on the normal side, this is going to be. Yeah, this is all going to be like this. This is equal to the n. So that's this part. So that's, and again, you're putting these into components, and these are just unit vectors. Remember, it's the same thing as k vectors. These are standard basis vectors, and these are also have magnitude 1. I mean, they're also length 1. So it's exactly the same thing, but now we're instead of using the xyz axis, we're looking at only the tangent and normal of the curve. It's actually quite fascinating here. So it doesn't matter what the x and y axes are. So it looks like that. And what I'll do now is I'm going to just use the graph from the calculus book. I'll just screenshot from there. I'll just take I'll just screenshot from that just because it looks a bit nicer than this one. And yeah, here, I just pause video and I removed my drawing. Now we have this drawing, so it looks again much nicer. And again, the length of these are 1. So this length is 1. And instead of ruining the drawing, what I'll do is I'll just write this here, the magnitude of t, like this. Yeah, the magnitude, because it's a unit tangent vector, and that one's unit normal because we're dividing by the same vector but the magnitude of it. This right here, the magnitude equals to this, the length. I'm not actually going to keep going, just extend it further because it's pretty interesting. It's the same thing as the length of the I equals to j, and again I put them all these here. Yeah, just go finally. I just like driving the point home because it's sometimes I need a reminder. It's unit yeah, they're all unit vectors, so they're all equals to 1. So all of them equal to 1. So keep that always in mind. So then this one here always has to be the same length. So then this one here, yeah, the t and the n have the same exact length. It's pretty fascinating. So whenever you draw it, you have to draw it exactly the same length, and so on. Yeah. So anyways, let's erase all these scribbles I did on this, and that's fascinating stuff. All right, now let's continue further. Now look at acceleration vector, the same one we're dealing with, but we're gonna now write it in terms of derivatives of the position vector. So instead of dealing with all of this speed and so on and so forth, yeah, we will write it strictly as derivatives of the position vector and its magnitudes and so on. So let's look at what the acceleration vector formula says. So that's this one right here. So this is the one I boxed here. So let's just write, actually this one here. So this one right here. So v prime, this is one in terms of the components. Like that. So I mean, yeah, v, yeah, the v prime, and then k v squared n. So we have the acceleration vector is equal to the speed, the derivative of the speed, times it by the unit tangent vector, then plus the curvature kappa times it by the v speed squared, times it by the unit normal vector. Alright, now the first thing to notice from this acceleration equation is that the binormal vector b is absent. So there's no the unit binormal vector. So right now we just have the unit tangent and a unit normal, but you don't have the unit binormal set up there. And again, recap on that as I went over earlier. So here is if you have a space curve like that, and there's a unit tangent, it's tangent to the curve. There's the normal, it's tangent, I mean it's perpendicular to the curve. So it's perpendicular, and it's actually going towards where it's curving in. And then the unit binormal is just a cross product of these two. So you take the cross product of unit tangent, a cross product with unit normal, and then you get and it's also going to be a unit length of 1, and that's also going to be, yeah, that's the b1. So there's none of that. So yeah. So if it's none of that, so then this acceleration vector is always going to be in this plane. Yeah. So it's always going to be there. Or not necessarily just in this area, but you could have -1, but it's always going to be in this osculating plane, and I'll illustrate that with a better thumbnail. All right, let's go back over here. All right, so right here. So yeah, first thing to notice is that the binormal vector is absent. So no matter how an object moves through space, its acceleration always lies in the plane of t and n. That is the osculating plane, which I covered in my earlier video. And recall that t gives the direction of motion and n points in the direction the curve is turning, as I just explained. So, yeah, so basically what you have is there's the oscillating plane is right here. So this is oscillating plane. So if you have a curve, and this is it from an example, there's the tangent vector, and then the normal is where it's curving inwards. So it's perpendicular to the curve, but pointing towards where it's curving. So it's curving inwards like that. And then this blue line is the oscillating plane all over that. And the other one is the normal plane. That's the normal one there. That's with a binormal and normal there. So basically acceleration is always going to be in this area. It's always going to be in this blue thingy. All right, and again, recap, yeah, here. So wherever the curve is going, so the unit tangent is always pointing in the direction of motion. So particle with increasing t goes always across there. And then there is the inwards. This one is direction of the turning. So the unit normal is going inwards. That's pretty epic stuff. So going further, so next we notice that the tangential component of acceleration is v prime, or the derivative of the speed. And again, that's the tangential one here, this one right here. So v prime. And the other one is curvature times v squared. So curvature times speed squared. All right, so Yeah, notice that the tangential component of acceleration is v prime, or in other words, the rate of change of speed. And the normal component of acceleration, kv squared, is the curvature times the square of the speed. This makes sense if we think of a passenger in a car. Yes, a passenger in a car. A sharp turn in a road means a large value of the curvature, so the component of acceleration perpendicular to the motion is large, and the passenger is thrown against the door. Yeah, because remember, it's acceleration's rate change of the speed. So for example, I'll just draw this all out actually. So if you have a road like this, and then so then this is the you have a car you're driving. Yeah, I'll draw a better car. All right, here I just pause it and fix up my car so it looks like that. And you're going this way, so you're gonna be curving. Or I'll just make a road like this. This is a road. Yeah, so you're going to be curving across. So the acceleration, going forward, basically tangent to this. This is the v. I'll do the velocity. Yeah, I'll do like this is a tangent vector there. Actually, no. Well, this one's I'll just put this is going to be. Let's say you have this is the rate change so you have basically the acceleration in this direction, and the tangent one's going to be actually the speed derivative of the speed. And then now you're going to have a much sharper turn inside here. You're going to have I'll put it like this. This is going to be much sharper. This is going to be curvature v squared. So as you're getting closer in here, you're going to be thrown all the way to the right. And because and that's because when you're going a straight line, the curvature is 0. So in other words, acceleration is 0. So then right when you start turning, the acceleration is going to be huge. Anyways, I just wanted to draw that out. Yeah, and then again, when you do a sharp turn, hence passenger gets thrown against a car door. Anyways, so high speed around the turn has the same effect. In fact, if you double your speed, so if you double it's increased by a factor of 4. Yeah, for example, if you were to go much, much faster, so if you have v equals to 2, and then if you have, let's say initial v equals 1, you'll have v squared equals to, well, still 1. But if you had v equals to 2, then v squared is equal to 4. Yeah, so which is much higher, and this makes sense because if you were to go very, very slow along a curve, you can make it, but if you were going very fast, you're basically, your car's going to flip over. All right. So although we have expressions for the tangential and normal components of acceleration, it's desirable to have expressions that depend only on r prime, and r double prime. So in other words, the derivative of the position vector. So to do this, and we take the dot product of the velocity v equals vt. Yeah, and this formula is, again, this is the velocity is equal to the speed times it by the unit tangent vector. That's the one we had earlier. Yeah, scrolling all the way back up, that's this first equation. So we have this first equation right here. So we take this dot product of the velocity with acceleration. So with acceleration as given by the acceleration vector equation, and I just added the components equation just because, Kepler's book reference to like the equation number, but I just like referencing it by describing it. So basically, we're going to take that dot product of the velocity with this right here. This is the vector acceleration vector components formula. I'll put this here so that you can just search it and in the notes and you'll see exactly what I mean. So if we take a dot product with that, and here's quickly pause the video and add some more notes here and simplify using the geometric equation of the dot product from my earlier video, as well as the properties of the dot product, namely property 3, and I'll show you that. So you can recap on the dot product. You just take the two vectors. Dot product is just the multiplication of the components and then add them all up to get a scalar number. And the important thing is that you have this setup here where it just equals to the magnitude of each dot product multiplied by, of each vector multiplied by itself and then multiply cosine theta. And when we're dealing with tangent or normal, what we get is we're going to get a theta. That is equal to 0 or pi over 2. Yeah, pi over 2. And where pi over 2, again, does 90 degrees. So things cancel out. All right, so that's why it's we're going to be using the dot product and going to cancel out a whole bunch of stuff. And also, again, we call it dot product properties. Namely, we're going to use this one here. So you can basically expand it out. Dot product of this with b plus c, the vectors, you can expand it out like that for that. All right, anyway, so what we have is v dot with a. In our case, again, v, remember, is just the speed times it by the unit tangent vector. Dot product with a is going to be the speed derivative, times it by the unit tangent vector. and then plus our curvature v squared, and then we're going to have a normal vector at the end like that. All right, so that's what we have. All right, so now that we have this, and yeah, now we can just use property 3, just expand this all in there. So we're gonna get the setup is gonna equal to v prime to multiply this inside, and then we're gonna have a it's gonna be basically, because those are just scalars, you could take those out again as by this one here. You could take the scalar out or in, you can move it anywhere you want. So we're gonna have now times it by we're gonna have, yeah, I'll just put it like this: t vector dot product with itself. All right, and then plus, next setup is, well, we have the v inside there. We're going to get a kappa v cubed. Then we're going to have a dot, this one's going to be a unit tangent vector dot with unit normal vector. So again, just using this property there, and then this scalars, you just get them all out of that. So that's what we have. All right, so yeah, that we have that. So what we have is, well, look at this setup right here. So these are a tangent and a normal. So those are basically perpendicular to each other. So what we're going to get is a setup like this. We're going to get a Tn dot with n. This equals to just using the geometric equation, this one right here, the magnitude of each one. Magnitude of t, and the magnitude of their unit vectors, so they're just 1. Yeah, like that. And then cosine, well, it's pi over 2. And that's because they are right angles to each other. So these are basically right angles. Yeah, these are just right angles like that. This is going to be the normal. And this is going to be the unit normal there. No, I mean unit tangent, and I just moved it over there. So again, that's why we have it there like that. So that's perpendicular. And what that means is, well, this is equals to 0. Yeah, this is going to be equal to 0. Yeah. And lastly, and I'll draw the I'll recap on the graph for cosine soon. But then this one here, this is going to be t dot. Yeah, this one's going to be, well, that's going to be the magnitude of this squared, and it's equal to 1. So this all equals to 1 because it's a unit normal. I mean, it's a unit vector. So they're all, because you're dividing it by the magnitude. So you have the vector and divided by the magnitude of it, you're going to get the just length 1. Alright, yeah, just multiplied by itself, and then cosine, well, it's 0. Yeah, it's cosine 0, and that is, and this one's going to equal to 1 now. Yeah, this equals to 1. And again, it's cosine 0 because you have, well, this vector times by itself. they're both parallel. So you have t by itself, yeah. So the angle between it is 0. So the angle between these two vectors, there's the angle, there's theta. Yeah, angle between the two vectors. So if it's perpendicular, it becomes pi over 2. And if it's 0, if it's parallel, it just equals 0. So in other words, it equals to 1. So this whole thing equals to 1. Box that out. And yeah, this whole thing equals 0. So in other words, this, I'll put it above here, actually, further away. This equals to 0. And again, just recap. Yeah, recap on the cosine. I think I've done it before, but I'll do it again anyway. So recap cosine. You have theta. This is cosine. Then I'll just recap. And then it looks like this. Yeah, so there it is. It starts off at 1. It goes to -1 here. So low is -1. And it starts off the origin, 0. And this is going to be pi over 2. Yeah, and then, yeah, that's pretty much what we have. Pi over 2 is 0, and it goes like that. And I'll draw this a bit better. It goes like this. Yeah, something like that. Alright. Alright, yeah, so now that we have all that, well, we could just solve this now. Well, this goes to 0. So all we're left with is just this. And the other one's equal to 1. So this just equals to 1. So we're just left with v times by v prime. So what I'll do is I'll move this whole thing down. So I'll put an arrow. Let's do it like this. Yeah, so this equals 2. I'll move it like that. Yeah, so that equals 2. We're going to have, put an arrow like this. This is going to be v acceleration, velocity, dot with acceleration. So the dot product of the velocity times velocity with acceleration, this equals to just v times v prime. So then we're going to move this over to the other side, because what we want is, well, thus we want the acceleration tangent component, which just equals to v prime. This just equals to, well, v dot a divided by v. So we move that over and recap on this tangent vector, the tangent component. That's this part right here. This tangent, that's a normal component. And again, recap how I wrote this. So a of t is just this tangent component there, this one here. And then the normal one is going to be k times v squared. In other words, curvature times speed squared. All right, so then we have all that. All right, so we have this. And now we know what these all are, because remember, we want these in terms of derivatives of basically that only depend on the position vector, derivative of the position vector, and the second derivative of the position vector. All right, so this just equals to, well, speed. The velocity is just, well, we know the velocity. That's just the derivative of the position vector. So that's just going to be r prime of t. So we're going to do a dot product with, and then acceleration is just the derivative of the velocity, or in other words, the second derivative of the position vector, then divided by the speed, which is just the magnitude of the velocity. In other words, the magnitude of the first derivative of the position vector. Like that. This is going to be like this. Alright. And now, now that we have all that, what you can do is box everything. I'm just going to box this in, actually. I'm just going to box this in. Alright, so that's what we have. Alright, so now that we have this is the tangent component, now let's take a look at the normal component. And so basically, using the formula for curvature given by the earlier video thumbnail above, we have, and I'll get to that in a bit, because remember, this is going to be our normal component of the acceleration. This equals to curvature times by the speed squared. So, well, we know speed is just going to be this one here, then we're going to square it. But let's get to the curvature. Recall the curvature formula from the thumbnail of my earlier video all the way back up above, I think here. Yeah, arc length, this is the arc length, and curvature, this is curvature right here. So there's a link to that, and then there's the formula. So curvature is just defined as a derivative, the magnitude of the derivative of the unit tangent vector with respect to the arc length. And then I showed that it equals to this setup here. It equals to the magnitude of the derivative of the unit tangent vector with respect to time divided by the derivative of the position vector with respect to time. And then I showed that is equal to this giant thingy here. So equals to the cross product, the magnitude of the cross product. Again, these things outside mean the magnitude of the length. Magnitude of the cross product of the first derivative of the position vector, cross product with the second derivative of the position vector, divided by the first derivative of the first derivative of the position vector, magnitude of it, and then all cubed. All right, so that's quite a mouthful. I'm going to put this all the way down. So what we end up having is, so this equals to, so notice this one is dot product. This one's going to be now. This is a dot product. Now it's going to be a cross product. So we're going to have a, this is going to be the same thing. Same thing as this one here, actually, but cross product. So it's going to be like that of t cross with this, the second derivative of the position vector r of t. Divide this by, and now there's a cube part. So this is going to be divided by the first derivative of a position vector, and its magnitude, then cubed, and now we're going to multiply by v squared, and v squared is equal to just this part here, and then cubed. It's squared. So we're going to have the multiplied by the first derivative of the position vector, its magnitude, squared, and then in other words, the same thing as this one, so this just cancels with this, we're left with the 1. So I'll just erase these just so it looks nicer. And then those just cancel out. We're just left with equals to, it equals to actually exactly the same as this, but the magnitudes, and it's a cross product instead of a dot product. So that's fascinating stuff. Yeah, but they also give scalars, because dot product gives a scalar. Cross product gives a vector, so we need to get the magnitude of that. So this is going to be just r derivative vector cross with the second derivative of it. Alright, and divide this by the magnitude of this one here. And that's it. So that is just going to be our an. Normal component like that. So box this whole thing in. Alright, and yeah, now we got this. Now we can go to the last example of this video, and it's going to be on example 7, tangential and normal components of acceleration. So if we have a particle moves with position function r of t equals to t squared, and then t cubed. Alright, now we're asked to find the tangential and normal components of acceleration. Alright, so let's put this all down there. So let's write these in their IJK formats. So here's the solutions. We're going to get r of t is equal to t squared plus, this is going to t squared I vector plus t squared j vector plus t cubed k vector. All right, so that's what we have. And now the derivative of this, because we basically need to know all these. We just need to know, basically we need to know the first derivative, second derivative, and then the magnitude of this one right here. And then afterwards, we're going to take the cross product and then the dot product of those and so on. So that's what we need. Yeah, so let's take the first derivative. So r prime of t, this equals to, put the 2t, so derivative of t squared, 2t, I, and then plus, again, 2t, j, and then this one's going to be now plus 3t squared k, like that. Last, the next setup is, I'll put an arrow like that. Next one's going to be, I'll ignore the arrow. I'll just put it like that. Just double. Now the second derivative, it's going to be the derivative of this one now. It's going to be just 2i, derivative 2t is just I, and this one's going to be, well, 2j, and then next one's going to be, well, this is, put the 2 down, so 6t k, like that. All right, and lastly, what we need is the this part here. This is the magnitude of the first derivative. So that's going to be like this of t. This equals 2. Well, you just take the square root of the components. So 2t squared. So we're going to go 4t squared plus, now again, another 4t squared. Then plus, this is going to be, well, 9. 3 squared is 9. And then this is t4. Now, these just add up. This just equals to, well, 8t squared. So this equals to square root 8t squared plus 9t to the 4. Alright, so now we have this. So therefore, the earlier formula for the tangential component of acceleration gives, and that's this one right here. So this right here, dot product of the first, second derivative, then divided by the speed there, magnitude of the first derivative. So let's take a look at that. So this is going to be now the AT is equal to, the dot product of the first derivative with the second derivative of t, divide this by the magnitude right there of the first derivative of t, like that. This equals to, so this equals to, well, dot product, again, you just take the components and multiply them and add it all up. So 2, we're going to have this 2t times 2, that's going to be 4t. So put it like this, 4t. Next one's going to be, well, this 2t times by 2, that's going to be also 4t. All right, and then lastly, this 3 times 6, that's going to be, well, 18. And then t squared times t is going to be t cubed. And then this 4t plus 4t, this equals 8t. And then this divide us by over here, this part is going to be, well, 8 t squared plus 9t 4. All right, and we'll just put this together now. So this just equals to, put it like this. We'll put it equals to, put this AT equals to 8t plus 18t cubed divided by square root 8t squared plus 9t4, and then box this whole thing in. Alright, and now going further, so the equation for the normal component of acceleration gives, and again now it's going to be the cross product setup here. So we're going to use this. It's a cross product of the first derivative of the position vector with r double prime there, and divided by this is going to be just the bottom part of this is just the magnitude of the first derivative of the position vector, in other words, the speed. All right, so let's put that in. But before we solve that, I'll do the cross product first. Since what we have is this is going to be r. Just do the vectors one. Then r prime cross with r double prime. So write this in our cross product setup. This equals 2, and I'll move this down here. I'll move it like this. This is equals 2. This is our I component, and then I component, J component, and then there's our K component. And let's write our I component. That's just going to be, well, this is going to be 2t, and then there's a 2t, then there's 3t squared. So 2t, 2t, 3t squared. Just write it in. And this way it's easier to, and this is the determinant form. It's easy to solve it like that. So now the next setup is going to be the double prime. So 2, 2, 6t. It's going to be 2, 2, 6t. Now we got to get the cross product. All right, so let's take a look at this cross product. So again, recall the easy way to memorize, cross these out. Then we're going to multiply this by this, and then subtract it by these two. So this equals 2. I'll put it like this, equals 2. We're going to have 2t times 6t. That's going to be 12t squared. Then minus by 2 times 2 times 3 is 6. And then t squared. This is going to be our I component. And now plus the next setup is going to be, now we do the other way. So we cross out this middle one, but now this one's going to be a minus now. That's the only difference if we put a minus now, and then put this here. So we're going to have this 2t times it by 6, and then minus these ones here, 6t. So 2t, 2 times 2 is 12t squared. Minus now we're going to have a 2 times 3 is 6, then t squared. Like that. And this is our J component. And here, yeah, quickly just moved everything over here. Just paused the video and moved it. So now the last part is we cross out the K section. So I'll cross this out. Yeah, here, my pen was just frozen. Here, I'll fix that up. All right. So, yeah, now we'll cross out this K part there. Now we're going to multiply this by this, 2t times 2, then subtract by these two. So what we get is, this is going to be now plus. And now 2 times, 2t times 2, this is going to be 4t, and then minus now 2t times 2, so minus 4t. And that's just going to be our K component. So in other words, this just cancels out. Yeah, this just cancels out. Goes 0. So yeah, those just cancel out. Yeah, so what we're left with now is, this just equals to now, yeah, this equals to this one here, 12t squared minus 6t squared. That's just going to be 6t squared. I. Then minus, this one's going to be 12t squared minus 6t squared. That's going to be, well, just 6t squared. So 6t squared there. Yeah, 6t squared and then j. Yeah, so that is our cross product there. All right, yeah, so I'll put here. So since we have this, now we can solve for the equation for the normal component of acceleration. Again, just go back to that equation here. This one right here, cross product, the magnitude of it, and then divided by the magnitude of the first derivative. In other words, the speed. All right, so let's put that all in. So thus, yeah, so since then, I'll just put it then instead of thus, mix things up a bit. So we're going to have now the A normal component equals to, this is going to equal to the cross product of R of t, the first derivative, R of t with the second derivative of the position vector, the magnitude of it divided by, divide this by the magnitude of the first derivative or the speed, like that. So now this equals 2. Yeah, this equals, so I'm going to move this actually a bit down so I can see if I can fit it in one line, or a lot of it in one line. So we have this equals 2. Yeah, and this equals 2 using, again, just using the length formula for this cross product magnitude. That's just using the length one is just going to be square root of now the squares of these components. So 6 squared is 36. T squared is going to be, t squared is going to be t to the 4. And then we have a plus. We just add the components squared, so it's going to be again 36 again, t to the 4. Then divide this all out by r of t. This is this part right here. Yeah, this is the the r prime of t magnitude, so the speed. So it's going to be square root 8 squared, and then 9, then 9t4. Right. So we're going to get a 8t squared plus 9t4. All right, now we can simplify this top part. We can just take out the square root 36, factor it out, and then factor out the square root t. The t4. So square root t4, and then what we're left with, well, is a 1 plus 1. So 1 plus 1 is just going to be 2, so I'll just put a 2 there. Yeah, I'll just leave it 1 plus 1 just for completeness. And then divide this all out by square root 8t squared plus 9t4. And lastly, what this all equals to, well, the square root 36 is going to be, well, 6. And I'll put this square root 1 plus 1 or square root 2 in front. So this one's square root 2. And then this one's t4 square root of that is just going to be t squared. Then divided by square root, I'll fix this up right here, 8t squared plus 9t4. Alright, and yeah, we'll just box this in, and that's pretty much it for this example and this video. So that's pretty epic stuff there. And yeah, so that's all for today then. Hopefully you enjoyed this epic long video, and again, yeah, pretty epic stuff here. I'm gonna, again, as always, I'll be putting these all in article format on the Hive blockchain and note format. Yeah, just in article format, as well as this will be available in PDF format as well. All in the links in the description below. And again, I'll be clipping all these into short clips, put them on the giant playlist and so on. So in case you want to watch or reference specific parts and so on. Anyways, yeah, that is all for today. And I scroll all the way back up. It's quite extensive. It's actually much more extensive than I thought. And then the next time I do one of these would be on probably on Kepler's laws or something. Anyways, or the associated Legendre function. That's something else. Anyways, that's all for today. Thanks for watching, and stay tuned for another Math Easy solution.